All right, August 2nd, machine learning with Dr. Mike Ellis from UCA. Take one.
And Don, take one. I thought we were doing one take. And Don, if I'm going a little long and we need to take a break, then please remind me, because that too, I'm not always keeping track. Okay, now I can see my clock there.
I certainly will. So you got sharing capabilities. So
yeah.
And I'm recording, so just take it away.
Okay. Since you made a comment about that I was to blame for the Monty Python humor, I have to do this. It's Doune Castle in Scotland. It's where many scenes from Monty Python and the Holy Grail were filmed. I visited there a few years ago. So anyway, if you have any familiarity with it might look a little bit familiar, but there's pictures inside that are that would be very familiar. Lots of scenes were shot, and they do this in the movies all the time, of course, where they point the camera one way and they shoot a scene, and then they point a camera a different way and shoot a scene, and they're supposed to be, on the other side of the world. And so anyway, that was interesting. It's a small working castle. It was the only place they could get into. So anyway, all right, well, good morning, everybody. Like I said, if we run into something where you've got a question, just go ahead and unmute and ask it. I'm going to talk about some general stuff at first. So if you're still downloading and unzipping the files, you're fine. I'm going to talk some slides. First of all, and we'll get into the notebooks after a little bit. So there are some blank cells in there. Some of the, what I always say, more typo prone code I left in there, but we're going to do some typing and look at some stuff and see how things go together. And, same thing, like I said, if I'm running late and we need to take a break, please, somebody say something. I don't have a problem with that either. So let me see, I didn't bother to open up my first set of slides. And I have individual window. Okay. So as I said, I'm going to start with some terms and concepts and things from machine learning, not so much the Python stuff. We'll talk about that as we get into the code. And then it's not cooperating with me here. There we go. So we'll talk about some machine learning terminology, some really basic stuff, and then give you a process to use. And then we'll have the specific machine learning techniques. We're going to start with k-means clustering, which is an unsupervised technique, which we'll talk about what all that means too. And then we'll do k-nearest neighbor classification, which is where we want to predict a category or a class. We'll also talk about decision tree classification. So they solve the same kinds of problems, but from a really different approach. And then we'll finish it with a linear regression problem, which is going to predict a numeric variable. When I talk to people at conferences and stuff, when we talk about linear regression, they say, well, that's not really machine learning. It's like, yeah, it's not, except that whenever you talk about machine learning or analytics or data mining or whatever the term is available that's related to that, linear regression comes up. It's one of the most often used techniques. So we'll talk about how to do that in Python especially. So the biggest thing I want to do, and I'm not going to spend too much time on this, so stop me if you want to talk about this a little bit more, but machine learning is using those algorithms in order to get predictions or help make decisions, find patterns in data that aren't really obvious if you're just looking at the data, and that also don't require you to go in and guide the process. You can set things up and then go, and that's what we refer to as the learning of the machine. We take previous experiences, that's the data that we have, and then we use that in order to perform better on similar decisions in the future. And so we'll see when we go into classification and predicting things where we already know some results that we'll have training data that we use to create the model, and then we use test data or data without any predictions in order to look at how the model actually works. Like spam identification, we're not going to do any spam text stuff today. In fact, we'll talk about later about how many things we're not doing today. We're just getting a taste. But one of the things that you do is look at, and you do this as a person as you're looking at email, and I am getting so many spam text messages on my phone lately. But you look at messages that are said, okay, this message is spam, and then these messages are good. They call them ham a lot of the time. So if you can create a model to say, this is what a spam message looks like, then you've got a pretty good chance of identifying that in the future. And that's really the kind of things that we do in the supervised type of machine learning. And you'll hear it a lot of times with AI, and sometimes it's at the core of AI, but AI goes a lot further. So I mentioned finding meaningful patterns in our data. So the first thing we want to do to get those meaningful patterns is we want to understand what's going on in the data. How are all these variables related? And then we also want to generalize that so that we can use it to predict in the future. A couple of things to keep in mind, or actually one big thing, is that the model is just a model. Almost made a Holy Grail reference there. It's only a model. It's just a representation of the relationships. It's not reality. So it's just an approximation. And we're going to talk about what that means as we go on today. So I've already mentioned supervised and unsupervised. It's actually pretty straightforward what the difference is, but it still gets a little confusing. So supervised is we have a target in mind. We're trying to predict something specific. We're trying to predict customers that will leave our mobile phone business, that will churn, or customers that would be a good credit risk versus a bad credit risk. With unsupervised, we don't have a specific goal. We're just trying to see what's in the data. So we have all these customers. Can we find some groupings of them that maybe make sense? We're not trying to find specific groups. We're just trying to find groupings. So really in unsupervised, we're creating knowledge. I mean, we're doing that to an extent in all of them, but in unsupervised, it's brand new stuff. So as I mentioned, we're going to do a couple of classification methods. It's really considered the most widely used type of data mining or machine learning, that and linear regression. There's a lot of different methods. We're going to use k-nearest neighbor and decision trees, but there's logistic regression, naive Bayes. You can use neural nets to do it. I'll show you when we go to some of the documentation pages that there are lots and lots of different methods that we're not going to talk about, but we're going to talk about the basics, and then you could take that and apply one of those other methods if you needed to. And then we'll predict some numbers at the end with regression. So there's unsupervised techniques. Association rules is often called a market basket analysis. That's another interesting thing. That's the people who looked at this item also looked at these items, or that bought this also bought that. You see on Amazon and other sites. We're going to do k-means clustering, like I said, in just a little bit. But let's talk about some of the terminology. So feature is a property that might be useful. It's also considered a characteristic. When we look at in fact, we'll talk about that in the context of an example as well. It's an instance of the unit of observation. So if we're looking at a table of data, which we often are, a feature is going to be one of the columns that we might use to predict, and an example is going to be one of the rows. And a lot of times I'll use those interchangeably. And sometimes we'll call feature a variable, or it could be an independent variable if you get into more of the statistical research type stuff. So like I said, if it's in a table, column, variable, attribute, feature, it's really annoying. I get it that there's all these different terms for the same thing. A lot of it depends on the context that you're in. But in machine learning, then those columns are called features, and a row is usually called an example. Lots of times I just call them rows, but you'll see any of those terms interchangeable. And then the target in supervised learning is what we're trying to predict. And you might see that in statistical research as a dependent variable and the feature as independent variables. But we don't really use that in machine learning. So we have features and targets, and we'll do more of that as we're going. So don't forget that a model's constrained by its training data. So the model's only as good as the data. You might have heard garbage in, garbage out. You can't go outside the data. The model, machine learning model, doesn't have any common sense. So how many times you've been recommended a product you already bought? I get that all the time. I get stuff, Amazon wants me to buy something again that obviously is something you would only buy, once a year or twice a year. It's a big quantity or something. So there's no common sense that a person would have if they were doing this stuff. So models are getting better with a lot of stuff like handwriting and speech recognition, but you've probably seen places where autocorrect and speech recognition comes up with bizarre things that, based on what you said. Now, one of the things I just want to touch on this, there are a lot of ethical issues around machine learning, and we're not going to spend a ton of time on that. But one thing to keep in mind is just because you can do something doesn't mean that you should do it. Of course, that kind of applies everywhere, but especially it seems to be especially relevant in machine learning. There's a great example from 10 or 12 years ago of Target, and I'm not going to go into a bunch of details, but they were using their data to identify customers that were pregnant so they could market maternity stuff to them. And they basically did it at first by sending them a flyer saying, congratulations on being pregnant. And some of them hadn't told family members or anybody else, and it freaked them out, understandably. And so they dialed it back and did some other stuff. But there's questions about who does that data belong to? It's the Target sales data. Should they do this in the first place? So a lot of it depends on how you do it. But if you're interested in those kinds of issues, I recommend this book, Weapons of Math Destruction. Kathy O'Neill has worked for some big companies in New York doing a lot of this kind of modeling. And the main message of her book is that whole idea that a model is constrained by its training data. And she talks about some things like, you might think that the credit score model is completely objective, but it has a lot of bias built into the measures that go into it. So that's the same thing as you can create a model that looks on the surface like it's good, but if you're using biased data to build it, then you're going to get a model that's biased. So a lot of interesting ideas in there. So you might consider taking a look at that. The GDPR that was passed in Europe, which normally has an E on the end, and then California just recently passed some things. So there's a lot more of it in the news that you might get a chance to take a look at. So use the term machine learning. So we say that machines learn if they can perform a task better with experience. So there are really four components to that: the data, then abstraction, generalization, evaluation. I want to talk about all those each a little bit, and we're going to hit on each of those in the examples today. Now, the big thing with data is that you need good data. And you guys have already been working on doing some data prep and things, because we have to work in order to get data to where it needs to be, because you've already seen this kinds of stuff. You get dirty data. No matter where you get it from, there's going to be some kind of an issues. This is an example I use all the time. I'm not going to spend a bunch of time on it, but how many different ways have you seen your name represented? Because what I consider official name that I use in publications and stuff is Michael E. Ellis. I use Mike Ellis every day. Sometimes it's just Michael Ellis. So there's three different ways right there. You can put the PhD on the end or a doctor on the front, and there's a couple more. And so it goes on from there. So these are all different ways that President Obama has had his name represented. And one of the things I point out is Malia and Sasha's dad. I guarantee you, when you were a kid and you were on a soccer team or something like that people knew your parents as your parents, and they couldn't remember their names. So there's lots of different ways that people are known, and none of those is even his real name. His full name is Barack Hussein Obama II. So there's 9 different ways that you might have one person in a data set, and you have to clean that stuff up. I have students regularly in my classes that work at Axiom, and when we talk about this kind of stuff, they just nod their heads. I keep feeling like their heads are going to fall off their necks because they get credit score data and lots of credit record data, and they have to do a lot of this kind of stuff. And so do lots of other firms and basically anybody that gets data. So we're going to talk over here in this structured side. There's a lot of interesting stuff you can do with text and pictures and things, but we're not going there. So we'll talk about some numerical data with a regression, but we're going to have numerical data in the data sets that we're going to use. We're also going to have some categorical data. Most of it will be nominal, but we'll talk about ordinal too. And ordinal is just if there's some sort of an order to the data. I thought I had something in here, so maybe I have that elsewhere. But if you have like clothing sizes, small, medium, large, extra large, there's an order there. But if you have eye color, brown, blue, hazel, there's no real order there. It doesn't matter. So that's nominal. And we're going to see how to deal with that kind of data. What the next part, data is that first part, abstraction is the next, and that's where we want to create a model in order to take that data and convert it into a broader concept. So we take those concrete examples and turn it into a model that we can use, and we'll talk about this a little bit more. And then generalization is to be able to use that model, that abstraction, to infer about similar future situations. So we have to figure out what's the best one that we can use. One of the things that we're going to see is some heuristics that these algorithms use in order to cut through, because you could, in theory, let's just run all the models that might work and see which one works best. But that could take a long time. I mean, like weeks, if you have, especially if you have a big data set. So we try to use those things to speed things along, and we'll talk about generalization and abstraction a little bit more later. And then, of course, we want to be able to measure performance and see how we can evaluate. One of the things that I always talk about is this quote from George Box that all models are wrong, but some are useful. And that goes back to what I was talking about, that a model is not reality, it's just an approximation of reality. So we're going to see in supervised training, we're going to have our supervised models, we're going to have training data, and then we're going to have test data that we know the result to, and we can actually evaluate. And we'll talk about this a little bit more later. And then as we do the test and evaluation, we might go back and correct our model or make some changes to try to get a little bit better. So a lot of times in evaluation, we have noise, because that's one of the reasons why it can't be 100% accurate. That's the idea that all models are wrong, is that you just can't know everything that goes into any kind of a decision. So if you do get 100% accuracy or close to it, that can be what we call overfitting. So the model fits the training data so well that you can't generalize it. So you get an abstraction, but it's specific to that data. You can't generalize it to new data. It won't do you any good. You can also underfit a model, although it happens a lot less. But you can imagine that if you have a model for some complex issue, let's say for student retention that universities are already interested in, and you just look at 2 columns of data, well, that's going to be a horrible model, because there's too many things involved in what happens there. So just a couple of graphic examples of underfitting and overfitting. So this would be underfitting if we have these blue data points and we fit a line like this. You can see it only accurately predicts about 6 or 7 or 8 points, and the rest are pretty crazy out of there. So we could fit a model like this, and that's going to very closely fit everything, but that's not going to do any good with any new data. So we really want something that's somewhere in between. It's our Goldilocks situation that we see all the time. So a good fit is going to do a pretty good job on future data, but it's not going to try to get right on the nose of every single data point. So that gives us a useful model. It's not correct. It's not right. It's not 100% accurate, but it's useful. So I mentioned that we're going to talk about a process. There's the CRISP DM is kind of the standard. There's a couple other models. They're all very similar. So we're going to talk about doing this. We need to understand the what's the business understanding is really what's the problem we're trying to solve, what's the context. We're going to assume that we know that you're in whatever business you're in. If you're in a bank, then we know we're trying to identify, potential credit customers and all that. The next step is the data understanding. You got to know where the data comes from, what it looks like, and all that. And then data preparation. And it's not really lined up. That's supposed to point straight at data preparation. A lot of it, and like I said, I know you guys have been doing this. And when you get into getting some wild data, you'll find out why we say it can account for about 80% of the total project time. So we get our data ready, and then we can build a model and test it and then deploy it if we put it out for people to actually use. And it really is kind of both a science and an art, and I think you'll see some of that. We always want to go straight to the model building because that's the cool part. But like I say, it's a painful mistake because you just are going to run into more data issues. So you really want to do a good job of cleaning up and preparing your data before you do it. And actually, we're going to find that creating the model winds up being kind of trivial. So these are my key takeaways from here. So feature, target, and example, we're going to talk about those multiple times. Data prep is where the work is. Creating the model can be trivial, but interpreting it is crucial. And that's where the contextual experience comes in, understanding the business problem and what you're trying to do with it. So, as I said, we're going to first talk about some common data prep tasks, and then we're going to get into unsupervised learning and 3 supervised learning examples. Let me get in. I'm pretty sure I didn't have this one set up right either. Yeah, forgot about that. Okay. So as I mentioned, and I know, well, does anybody have any questions? I said I would pause, and there I didn't.
Everybody good?
Okay.
Everybody, just real quick, Whitney is also an apprentice, but doing a specialized thread in business intelligence development using Tableau. So I asked her to come in, and she's not a normal part of our group, but she is a member of the ACDS apprentice family.
Okay.
Welcome, Whitney.
Tableau is a really interesting program. You can do some pretty cool stuff with it. I'm not really using it anymore, but Dr. Thomas, who does it in our BI class, just did a big time Tableau training program this summer. So we're looking for some interesting things to come out of that. So you guys have been doing the general data cleaning, probably been doing some missing value stuff too. We'll touch on those as we go through. But the 2 things that you probably have not been doing is rescaling the data and then dealing with categorical data. So we'll do those as well. So we've already talked about that. Just remember with missing values that there's more to just filling in some data, some blanks with some kind of a data. It isn't always obvious that you have missing values, and I'm going to show you that in one of my examples. And then how are they represented? They can be different. I did in my doctoral program, I worked with some people in psychology, and they used -999 for missing data. I don't know why. That's just the standard there. So it depends on the software and where you are, why they're missing, because you can have them missing on purpose, and then what you're going to do about them. But rescaling and the categorical is what we're really going to get into today. So the idea, and you'll see this in the examples, is that when you have features in the model, they should be on the same scale for most of the machine learning techniques. That's not true with decision trees, but for most of them, they should be on the same scale. So what do I mean? Is if you have one feature that is income, and you have values that are, let's say 30,000 to 75,000, and you have another column that is months at this address, and you have values from 1 to 30, those are very different scales. And so what will happen is the income will have a much bigger impact because the numbers are bigger. So we put those on the same scale, and we'll do that in our examples, so you'll kind of see the difference. Also mention the categorical data. This is the slide I was thinking about. So we'll see nominal. We're going to have nominal stuff. We're not going to have ordinal. Sometimes that becomes an issue, but you can make a mistake and turn a nominal variable or a nominal feature into an ordinal feature. And so we'll talk about that a little bit too. But the way we take care of the categorical variables is called one-hot encoding. In statistical research, it's called creating dummy variables. It's the same thing. We even use there's something built into sklearn that's called one-hot encoding, but we're going to use get dummies from pandas because it's just much easier. So what we do is we convert a categorical feature to multiple features, and then we have a 0 if it's not there or 1 if it is there. So here we have employee status or employment status, full-time, not working, full-time, part-time. We can't do any modeling with that. So what we do is we convert that into, we have 3 values. So we have a full-time, a part-time, and a not working column. And then the first row would be 1 in full-time and then 0 in the others. And that's how we handle the one-hot encoding. Now you can see that with like the second row, if it's not working, if it's a 0 in full-time and a 0 in part-time, then it has to mean that this person is not working. And so we can eliminate that one and just use 2 columns instead of 3. So we drop 1, and we'll do that in the examples too. So real quick, so what if you'll chime in here, what do we need to do to this data based on what we've talked about so far? Anybody take a shot?
Don't make me pick a name, guys.
Maybe that year's service, there's a 2.5 there, so then he's get rid of fractions in that column.
No, actually, that should be just fine. We might have decimal years, and that should be okay. That should wind up being a float value instead of an integer value, but that should be okay. What else? And I'm thinking more along the lines of the categorical, because I mean, salary and year service are obviously on different scales, so we will have to rescale that. But
what about the eye colors? You're changing them to the actual categories instead of the integers?
We could do that. Is there anything else we'd have to do to that? We would have to do the one-hot encoding too, right? Which even if we, and this is really kind of one of the big points I want to make here, is even if we just leave the numbers in there, it still should be one-hot encoded. But one of the things that we'll see, and we're going to do this in an example, is change numbers like that to the actual text values, because then we get column names like this. Full-time, actually it would probably be emp status full-time, but I didn't want to take up too much space. Otherwise, if we left the numbers, we'd have emp status 1, emp status 2, and that's really hard to interpret, and it's really hard to explain to your boss's boss what that means, and you got to go back, and then they're all frustrated. And so I like putting the actual terms in there, but we still have to do the one-hot encoding. What else might we have to do? I need to get a recording of the Jeopardy music. Yeah, somebody take a shot, or are we all just
you did cover, yeah. I know,
wandering away from our turned off cameras.
These guys, you almost got a call on them to make them come off mute, and like,
well, we heard from
participate,
Edgar and
doggone it.
Seth.
I personally would maybe change how the eye colors are in that like numerical. I would maybe make the mobile carriers like that, so then they're all numerical. You kind of addressed that with Edgar, but just to make it all numbers. But I don't know if that's the right direction.
Well, actually, like I said, I would put the words in for the numbers for eye color because you get a better description later. And you'll see that better when we do the example that includes something like that. But there is something that we'd have to do with the mobile providers. Again, we'd have to use the one-hot encoding to convert that into multiple variables.
And Mike, is that one hot encoding? Is that like a recommended step or a mandatory step in like the CRISP DM methodology
No,
checklist?
well, it's part of the data preparation stuff. I'm going to talk about general data stuff, which you guys have been doing, and then stuff specific for modeling. And
Okay.
that's what the one hot encoding with categorical variables is. It because you just I don't, at least in Python, there are a couple other packages that will deal with this Verizon, T-Mobile and stuff, because it'll do all that one hot encoding behind the scenes. But the way the Python stuff is now, you have to do it yourself, but it's not difficult. But you just look, oh, it's categorical. All right, let's do it. So you'll see we'll actually do it in like 1 or 2 steps. There's one other thing here, and it won't be obvious right now, but it'll hopefully be obvious later. And that is that we want to make sure that we don't use the ID column in trying to model, because maybe we're going to model salary based on some of this other data, or the mobile carrier based on this other data. But ID, like a name or a social security number or anything else that uniquely identifies each row, is really going to mess up the model. So a lot of times it'll come back that if you put in the ID, it'll give you a 100% accurate prediction. So we've just got to be careful about that. And so we'll drop that. So I just wanted to make sure that some of that stuff was somewhat straightforward up front.
Maybe getting ahead, but would using that as the index of the data frame take it out of the model?
Yeah.
Okay.
Yeah, and in fact, that's one of the things that we're going to do. We can do it a couple of different ways to deal with that, but that's one of them, is to do that, set it as the row index, because then like some of the data we're going to deal with, you might need to go back and find individual rows in there, so that helps you with it. So if that's a possibility, then do that. Otherwise, you can just drop it out, because a lot of times that's perfectly fine. Any other questions or anything? Hardly can hear myself with all the chatter going on. Like I said, this is weird enough talking without any comments or anything. So, you know, like I say, if I know we haven't gotten into much yet, but feel free to chime in. So the first thing we want to do is talk about k-means clustering then. So we look at it for identifying the natural groupings of things. Like I said, there's unsupervised learning, so there's no target variable. So we're just looking to see how do things group together. We can do a lot of different things. I mentioned about customer segments, but we can look at lots of different things. Even just look at labeling a population. We can actually use it as the first step, and then use the clusters we identified to create a classification model and see if new customers would fit into those classifications. We can look at identifying outliers, where all these groups cluster together, all these data points, but then some data points don't. And it's like, those are outliers. So maybe that might be a fraudulent activity, or it might be something else. So there's lots of different ways that it can be used, but it's pretty straightforward. So one of the more common ways of doing it is k-means clustering. There's hierarchical and other ways. So the k is the number of clusters that you want to create. Now, I said that we're not trying to do specific clusters, but we do need to tell our algorithm that here's how many clusters we want to create. So we do that before we do the analysis. And then what we do is we look at the data points and use distance between the points in order to assign clusters. So it has to be numeric and standardized, and you can't have any missing data, because then you wind up with an infinite distance, and it doesn't like that. Now, again, some tools will take that into account, but right now the stuff in Python does not. I kind of like that, because it does force you to really clean up your data before you start modeling, so you don't have some assumptions that kind of fall through the cracks. So we'll talk a little bit more specifically about distance with the k nearest neighbors on the clustering. So how do you determine the k value? That's always one of the questions that comes up when we start doing this. I start, well, let's use k equals 3. Let's use k equals 7. One of the things is domain knowledge. So we can talk about, we just know that in this instance, there's normally four clusters, and we want to identify those in our data. Also could be business requirements. We could be looking at clustering customers, for example, in order to do some marketing. And we say, well, we're going to create 3 marketing programs. So let's figure out which customers would be the best that we might use with each one. So let's try to cluster our customers into 3 clusters. So it could be that simple. You can also just experiment and find the best way to do it. Find the most homogeneous groups. We're going to talk about silhouette coefficients later, so it gives you a feel. You can also use something called the elbow method that we're not going to go into. But the bottom line on K is usually the best thing is to get something that you can use instead of spending a bunch of time trying to figure out if 7 gives you a lot better model than 5 or 9 does. So keep that in mind. The example we're going to use uses some, I guess we would call it domain knowledge. So we'll see that a little bit. So this is how the algorithm starts or works, and we'll do that before we get into the code. So let's see. So we select k points as centers. So we pick the k points, and we can just do that at random. And then we assign each point to the nearest cluster center. So we look at all the points and we calculate the distance between the points and each center. And then whichever the lowest distance is, that's the cluster it's assigned to. And then we have those clusters. Now we recalculate the new center, and then we repeat that until we get to some sort of criteria. Usually the clusters become stable, or we may have some other way of doing that. So let me show you a graphical example. So these blue diamonds, sorry, are 5 points chosen at random as cluster centers. So then we look at all the points and calculate the distances between each point and each of those 5 centers. And then we look at which one is the shortest value here, the shortest distance. So the pink ones are all here, and there's only one black one that's near this center, and we've got green and red and blue. And so we've created those clusters. So you see the pink cluster was created with this center way out here, the nearest points. Well, now we have all of these are pink, and so we calculate a new center, and it's going to be around here, and then we redo this. And so a couple of these green ones might move into the pink cluster, and we repeat that. Now there's a pretty good online example, and I'm going to have to switch my screen that I'm sharing here. Where did it go? There it is. And so you've got that link in the slides if you want to take a look at this. So you see this is over 8 years old, but it's no big deal. It's a visualization. So what you do is you can pick, how are you going to randomly pick it? You can pick uniform points. Gaussian mixture means normally distributed. You can do these different ways. Let's just do Gaussian mixture. So there's the data, and then we're going to add a centroid. And so how many are we going to add? There we added 1, 2, 3. Let's actually make it 5. So it makes it a little more interesting. So yellow, you can just barely see down there. Now, if we hit go, it assigns everything to the nearest center. And then if we update it, you see it shifts the center a little bit. And then now it's going to reassign points. and it'll keep doing that till it stabilizes, and it's pretty close to stable now. So you see, it didn't take, I think I see a green turn to yellow. Some more. So it is shifting a little bit. So it's taking a little bit longer. So but even then it didn't take too many now it's stable. So let's actually look at randomly and uniform points. That's more interesting. And we'll just add 3 centers. And same thing when we go, now it's going to assign everything to the nearest center. Now it's going to update the centroid, and you can see like the blue one, the center is going to shift over to here somewhere. The green one is going to be like around here, red one. So we'll see those move quite a bit. Yeah. And this will actually stabilize pretty quickly. So you see it goes through that process of calculating the distances, assigning it to the nearest center, and then recalculating the center and doing it. And it doesn't take too long in a lot of cases for it to stabilize. Now, if we went in here and did like 11 centers, it would move around quite a bit for a while. But just a little graphic way to see how that works. It has a description of the algorithm and everything in here and some of the properties. So, and you can restart it and do it lots of different ways. So if you want to look at something to get an idea of how that works, then that's a pretty good way to do it.
Hey, Mike.
Yeah.
Couple things. We're coming up on a logical break.
Sure.
Time wise, I mean, not necessarily curriculum wise, but there's something fundamental in my understanding that I'm losing a grip on, and that's the number of features, which are just columns, attributes of.
Right.
I've lost track of how many features we're examining in this algorithm, in this k-means clustering. Is it like correlating 2 variables or 2 features?
Well, this is the data point, and it can be defined by as many features as you need to. We're gonna see that like I said, I'm going to talk more about the distance in the nearest neighbors, but we calculate the distance by taking the difference between all the different feature values and
all the different. Yeah. So this is like correlating.
Yeah. So this is just showing
many
it
features
in
you
2
have.
dimensions. Yeah. And yeah.
Okay.
So yeah, it's kind of simplified. So let me just finish this, and I'll get the thing open, and then we can take a break and then jump right into the code when we get off of that. So
you got it.
So you've been using pandas a lot. We're going to use scikit-learn, and it's one of those confusing things. It's scikit-learn, but sklearn is how we actually call the package. So sklearn.cluster has the different clustering functions, and there are other ones, but k-means is the most common one, and we're going to use that. But remember, we still have to do our data prep and scale the data, and we have to deal with the categorical features. So we're going to start with some of that stuff. So I think, as I was just saying, that since that's a good place, that we can go ahead and take a break, and we'll come back and jump into that first k-means clustering notebook.
Perfect. Okay. Reconvene
Right.
at 9:30.
Okay.
Get up, stretch your legs, check your email, see everybody back at 9:30. All right. Welcome back, everybody. Second hour, machine learning with Python.
Okay. Let me make sure I share that. There we go. I was just working on trimming a couple things off of my screen to reclaim some real estate. So I'm going to turn off the header there and gain a little bit more. So, but I'm in the k-means clustering notebook, and so we'll start with that. Oh, I also was thinking that if you're looking at all the stuff that I sent you, and you're thinking that we won't get done until 3 o'clock this afternoon, that's not the case. there's a lot of data prep stuff, some interesting things in this example, and in the K nearest neighbors, and we're going to talk about distance in some detail, but the decision tree and the regression examples will both go pretty quickly. So let's get to it. So I have put where I think in every case a link to the scikit-learn site for whatever technique we're using. There's a lot of good stuff about them. You see the k-means for the clustering, and you can go, here's the overview of clustering methods, spectral clustering and hierarchical and DB scan and all this stuff. So there's, even with clustering, there's a lot of different ways to do it, but k-means is pretty straightforward and pretty easy to understand, so it's very commonly used. But you can see some examples and some other stuff here. So make sure that you go look at some of that documentation. And I mentioned the CRISP DM. We're going to take the business understanding as given, and the deployment, of course, we're not going that far, but we're going to kind of follow this this process outline here and start with data understanding and prep, and we'll trim those down as we go. So this problem is one that actually, Don, I don't think you've seen before. This is taken from the book Machine Learning with R, when the author was, I think, working on a master's degree at Notre Dame. This was some sociological research that he was involved in. And what they did was they sampled a bunch of US high school students in 2006 that used a well-known social networking service. They did not release what it is for privacy issues. It really doesn't matter to us. But at that one time, they sampled freshmen, sophomores, juniors, and seniors, and they used a web crawler to gather the data from the profile. So yeah, this is like on the verge of being creepy here. And then they used a text mining tool to create a set of 36 words that were in the profiles, and we'll see them here in just a second, and then the frequency that they're in the teen's profile. So anyway, what we want to do, and I left this in there, is we want to import pandas and read the data. So I'm going to go ahead and run that, since it's going to take me just a second. So we'll see with the info printout, we have the graduation year, and we have the gender and age and friends, and then starting with basketball through the end, these are all the keywords that they found. And you see that they really run the gamut here: basketball, football, cheerleading, cute, sexy, kissed, God, church, Jesus, mall, shopping, die, death, drunk, and drugs. I mean, we've got the gamut there in 36 keywords. And then, so those are the names of the columns, and then the actual data is going to be the number of times that those appeared in that profile. So my data frame name is teens, and so I want to look at the descriptive stats. So let's look at describe. But I don't know if you've done this before. If you add the capital T to the end, it transposes, and on a big data set like this, it just is a lot easier for it to show up. I'm getting the scroll bar because I've got my text big, but if you're doing it the normal describe, this would run way off the screen to the right. So instead it goes down and you can see the different things. So
cool.
Yeah, I use this almost all the time now. So you just have to add the dot capital T. If it's, if there's 5 columns, it doesn't matter. But when you get to some, it does. And I find that it's a little bit easier to compare some of the data here. So you can see some things here. First of all, most of them have a 30,000 count except age. So it's apparently, and we see this in the info up here. Oh, and gender too. I guess that didn't show up because that's a nominal value, but you see gender and age both apparently have some null objects in there. And remember, describe doesn't show categorical, but doing another example, you can do that. And you've probably done that already. So what kind of graduation year values are there? So we can look at the teens grad year and look at value counts and just double check it. It said in the description of the data that my computer's slow. that they sampled evenly across the different classes, and they did. So they have 7,500 of each of the 4 years in order to get those graduations. So what are the things that we would normally do pretty early on? And like I said, I know you guys have been doing some of this, but one of the reasons they're doing this is just to show that, yeah, we definitely need to do this in an analysis. So we can look at the correlation matrix and see what's there, but that's not very useful, is it? So hopefully you've looked at some in Seaborn where we can do it as a heat map. So I'm going to run these next 2 cells and it'll take just a second. Well, that's a little more helpful than what we had, but it's not all that great. So actually what I'm going to do is add some different options to this. And you may or may not have seen these so far. So one of the things I want to do is we're going to import matplotlib.pyplot. And this is something that I've just found as PLT. Just found with a little experience is that this helps us set some of the stuff on our correlation matrix. So the first thing we're going to do is in this correlation matrix cell, excuse me, is plt.figure. And what this does is allows us to control the size of the figure out here in the cell. And I'm going to set fig size equal to, and then we've got parentheses, and I make it 25 and 15. And there's nothing magical about that. That's just something I found through trial and error that seems to work pretty well in this situation. So then the other thing I want to do is I'm not going to end my parentheses there. It's going to end on a later line. So let's add a comma. We're going to add some more arguments to this heat map. So one of the things you see on this correlation matrix is it starts at whatever the smallest negative number is, somewhere here below 0, and ends at +1. But it would really work a lot better if it went from -1 to +1. So it would give us the whole range. So let's look at, we'll make V min equals -1. That's the vertical minimum. And then V max equals +1. You can just put 1. The other thing is this color map here goes from really dark, I don't know if that's actually black down there, but purple and onto light. It works better if it has a, was it divergent or convergent? I can always never remember, but maybe if it was a really light color in the middle and then different colors on the end. So we can change the color map using the option C map. And I like the option cool warm. Now there's lots of different color maps, so whatever you like is fine. There's another option called annote for annotate, and we set that equal to true. And what that does is it puts the actual values on the correlation matrix. And then there's one last thing that I like to do, and that is to add an option called line widths and set that equal to 0.5. And all that does is you see that this now, all those colors merge together. That just puts lines in between and separates everything. So it's a little neater. So I guess it's my latent accountant coming out. So then we need a closing parenthesis because I deleted it earlier. And then we add plt.show and parentheses and run that again. And we're going to use some of these types of options on some stuff later too.
I got a syntax error. Vmax. You got to say equals.
Yep. And I'm using this standard of just putting each argument on a different line, because I think it's a lot easier to find problems if there's nothing wrong, specifically with putting them all on one line like this. But it's I like it this way. One of the things, the the folks here are all out working in the world, but students, for some reason, I don't know if they think they're saving trees by not using more lines in the cell or something, but they want to jam everything on as few lines as possible. It's like, it makes it so hard to work with. So, but that's usually something you have to find out yourself. So in this case, we've got almost everything is right around, of course, the diagonal, everything's going to be 1. So that's going to be this extreme. But when we do this, then if we have some strong negative correlations, then they'll come out as a dark blue, or we have the dark red. But you see, all of these are in the middle. So nothing too strong in here. And you can actually see the values in some cases, in these cases. So we'll see with fewer features that it works a little bit better. But I like that versus the other view. Now, if you're just getting an overall view, it doesn't change things much, but we can take a look at that. Is everybody okay with that? Like I said, we'll use that again later.
So we're not seeing any strong bivariate correlations,
No,
but we are. So yeah, cool. So cool lead into why we're doing machine learning.
no, in fact, it looks like the biggest one is 0.5 here between marching and band. Big surprise. So in fact, for that reason, you could make the argument that use one or the other, you don't need both. But there, even with that, it's funny, it's still only a 0.5 correlation. You would expect it to be higher. So there's obviously, but there's other type, orchestral band and that kind of stuff. So anyway, yeah, so it's interesting how little it's actually correlated. So yeah, there's nothing that's just going to jump out at you here. So there are some issues. We saw that gender and age both did not have 30,000. You see that there's gender, there's some unknowns. Those are the null values that we saw in the info. And then in age, there's some missing, but there's also some outliers that are, just look like crappy data, basically. So we're going to take a look at those. So for the gender value, what we're going to do is actually create an unknown. So we'll have male, female, and unknown. So if we look at teens gender dot unique, we'll see that it has male, female, and a null value is all it has there. So rather than getting rid of those nulls, because if you remember from the numbers that we had there, there's almost 300, which is still just what, 1% of the data, or less than 1%. But remember, one of the things with missing data is that we want to make sure that when we're taking care of missing data, that we don't get rid of a bunch of other good data. So if we delete those rows, we're deleting 39 other pieces of data to get rid of one null. So better off to do something with it. And in this case, and in another example later, we're going to just create an unknown category for gender. So I left that code in here. What this does is it takes this dictionary. Have you talked about dictionaries?
Yes, we have key and
Okay.
value pairs. Yeah.
Okay. Yeah, so the key is gender, and that's the column. And then what's the value that we want to put in there? And I'm just going to put in a capital U because we've got capital M and F. And then use the fill NA option on the data frame and tell it what values are we going to do, and we're going to do it in place. And then when we run that, we'll get the value counts of gender, and we'll see that we now have, if you add those up, it's 30,000. So we've now got those filled in, so we shouldn't have any null values in gender. And same thing, if you run into any kind of an error or something and you're not getting it, stop me and let's fix it. We'll take 20 seconds to fix it versus you just being, like a fish out of water for the next 20 or 30 minutes. So let's take another quick look at age. So if we just look at describe on the age column, you'll see we obviously have some nulls because we have a count that's under 25,000. So we have 5,000 nulls in there, more than that. So that's a substantial chunk. So we need to do something with that. The mean is right about 18 years. That seems reasonable. But wait a minute, look at the min, 3, and the max, 106, almost 107. So there's obviously some bad values in there. Now, how does that happen? Well, if high school students are putting in their own data, they might have put in something wrong, or they might have put in a typo. You know, they might have, like 106, that might have maybe was supposed to be 16, and they just got a typo in there. And then I think that you'll see in the age values a lot of fractional ages, and I think they were putting in actual birthdays and calculating fractions of a year and all that stuff. So I don't know all the details on that. So how many of those null values do we have there? Oh, actually, yeah, if you do a box plot on teen age, it actually is kind of interesting looking. That's another way to take a look at that. But if we look at teens age and look at, say, is null, and then we want to get the value counts. So let's get all the places where it is null, all the true places, and then get the value counts. And we can see that we have 5,086 nulls, which we can know just from looking at this count number. And then we also know that we've got some values of age that are too low and too high. So let's see if we use a little subsetting. Let's look at the examples where teens age, whoops, is less than 13. So we've got some ages, you know, in the single digits here. At 12.35, that could actually be a valid value, except this was taken in 2006, and that's their graduation year. So they would have to be 12 and graduating that year. So they have to be a 12-year-old senior. That does happen, but probably not that often. So you see all these single digits. I don't know what's going on here, but we got some bad data in there for some reason. So it looks like there's 53 of those. Let me zip that up so we don't let that get in the way. And then let's take a look at the instances where it is, you can use greater than 19 or greater than equal to 20. So where it's big, so you see we've got some 100, almost 107, 84, 33. Now, those could all be legitimate data points. I don't think there's 384 of those in there though. So there's some issues. So there's another problem with our data, is that we've got a gender issue with nulls, and then we've got some bad data in the values. So one of the things we're going to do then is, and I left these a couple of lines in here so we can get to it, is we're going to get rid of those values below 13 or over 19. This where function replaces it if the condition is false. Now that seems totally backwards, but that's the way it is. So line 4 here will replace anything that's less than 13, the low values, with a null. And this one will do anything that's greater than 19. So if we run that, that will give us a null. And if we look at the results, now we've got 5,523 null values. And if you go back to looking at the counts on the ones that are low and ones that are high and add it to the ones that were null, then you'll see that that's actually correct. We can identify the different rows that contain a null age. Doesn't do us a whole heck of a lot of good. But what are we going to do with those nulls? So what the author who did this in his research did was, he said, well, look at the graduation years and what is the mean age of each graduation year? How about if we replace the age with the mean age of that graduation year? So that's probably about as good as you can get. And then that way you can keep this data. So this next cell, you see that if you're a senior, 18.65 years, junior 17.7. So it looks like there's about a year spread between those. So if you're just a freshman, you're just a hair short of 16. That seems right. So that's a pretty good way to take care of those null values. So this next cell does just that. It creates a little function here. And this is one of those things that it's for this situation. This is not a general thing, but this works in this situation. So define this function here that's going to get the mean of the group. We use a group by, and then it's going to fill those values in, and it calls the function here with the transform. And so there's a lot going on here, but it works. It does what we want it to do, and you can kind of tear it apart later if you wanted to go through and see all the different ways it works. But you see, in just a few rows, we can replace all of those null values. So I don't remember if we had one that was missing in the top rows, but by looking at the top and the bottom, I know in one of those cases, I've already forgotten, but there's at least a couple of rows in here that were null that we've now filled in with the average. So we actually now, if we did info again, we would have no null values in there. In fact, I'll just rerun this cell, and you see 0 rows have a null. So that's the kind of stuff that I'm calling general data prep, the things that we have in our data that we need to get cleaned up no matter what we're going to do with it. So, because here's one of the things that's going to strike you in just a minute is I'm not going to use age in this model. But in order to do some comparisons and look at the results later, you need to have that taken care of. So it's a really good idea to clean up all those just generic general data issues first, and then we're going to do the specific data prep for modeling. Does anybody have any issues or questions before I go to the next part?
Anybody got well, it's not a compiler. Anybody got a syntax error they want to come back and fix up? I'm successfully following along, Mike. So I think I've got a complete notebook so far, but if you could rezip your notebooks and send them to me, and I'll repost those as the complete, in case folks are getting behind or didn't have a chance, to follow along.
Sure. I would say in about 80% of the time, if you've got a problem when you typed in the code, either you forgot to close a parenthesis, you left out a comma, or you just typed something like when I type a word like teens that has 2 E's, sometimes I'll double the N's instead of the E. I don't know why. So
I kept trying to spell it T-E-A-N-S. I don't know why my fingers are.
So those are the things to look at. And the other thing is, remember, if you get an error and it says it's on line 5, is where the error, it might be at the end of line 4. Those are the most common things that I see, and you can usually catch those really quickly. Okay, so since we're doing clustering, it's unsupervised. So what we're going to do is we need to do the one-hot encoding on the gender, and we need to standardize our numbers. So we're going to do those two things and then create the model. So I'm using a generic outline here, and we're going to follow this where we're going to we call pandas. We already did it, so we don't need to do it again. But you're going to find that we're going to call the same common libraries in most cases. So we use this pre-processing standard scaler to standardize. We use metrics to evaluate the model. And then in there, we're going to use whatever the specific modeling technique is in order to, those are the libraries that we're going to call. So usually try to start the notebook with these. But like I said, we're going to approach these different. And by the time we get to the last one, it's going to be a lot tighter common code in it. So let's take a look at that. So like I said, we don't need to import pandas. If you want to include that, as a reminder, you can comment that out, or you can re-import it. It really doesn't matter. There's just no need to. So we want to use that standard scalar. And again, I've got a link here to take a look at that. There's in the pre-processing, there's a lot of stuff that you can do. So what we do there is we use this from way. So because we're only, sklearn is so big, and a lot of these different parts like pre-processing are so big that we just import different parts of them. So from sklearn dot pre-processing, let me see if the autofill will help me out. There we go. From sklearn.preprocessing import, and you have to capitalize standard and capitalize scalar as one word. So and then I'm going to, from sklearn.cluster, that's the part that has the k-means. So from sklearn cluster import k-means, and the k and the m are both capitalized. And then from sklearn, let's import metrics. Let me run that. That's going to take just not too long because we're just importing parts of it. Now we could just say import sklearn, but we're going to load so much stuff into memory. You know, like I said, you look back here at the sklearn stuff. Look at the user guide. Here's all supervised, unsupervised visualizations, transformations, all this stuff. So we don't need all of that. So there's no point in clogging up memory to do that. So as I said, there's a couple of things that we need to do. And if we use the standard scalar to standardize, we have to actually move some things around a little bit in order to make sure that it works out right. So this next cell, I've got everything there. So what it does is it drops the columns gender, grad year, and age because we don't want to standardize those. We don't need to. Gender is a nominal, and then grad year, you could argue grad year is categorical as well. And then age, we could standardize it, but we don't need to. And like I said, we're not going to use it in the final model anyway. We're going to use it for some comparisons. So we're going to drop that and then store that as teens temp. And then I'm going to standardize teens temp and then put the columns back in to basically reassemble the data frame. So I'm creating that temporary data frame here. And then we're going to create a standard scalar object. And this is one of those that this is a standardized way of that people use this. So we create using the standard scalar function, create an object stdsc, and then we use the fit_transform method that's built into that, and we do it on the data that we want to standardize, and it's going to do it and then save it as teens_std for standard, and then we're going to view that. So if I run that, we'll see that now it's all standardized. Now this way of standardizing, and I think I kind of cruised through that a little bit earlier, is what we're doing is we're doing a z-scale standardization. So that means we're taking each feature. So let's see, what was one of the basketball was the first one. So we look at it takes the minimum and the maximum on basketball, and then it puts that on a z-scale where the minimum is somewhere around -3 standard deviations below 0 and +3 above 0. And so it puts that in, everything will be on that same scale. So you see this will be the basketball value for the first person in here, the first row, and this will be the basketball value for the next one. And then the third one. So you see now they should all the values should be roughly between -3 and +3. See, here's one of the values for some feature that's 2.02. So that's a relatively high one. But it takes care of the problem that if the maximum on basketball was 5 and the maximum on shopping was 45, those are still very different scales. So it puts them on the same scale. So it doesn't give shopping a lot more importance than basketball. So that's why we standardize. Now, if it turns out these were all on a 1 to 5 scale, then we wouldn't have to worry about it. So it doesn't really matter if they were all on 1 to 100. It doesn't matter what the scale is. If they're all on the same scale, we don't worry about it. So you saw in that output, it's an array. And so one of the things that we have to do is we have to look at getting the features, and I'll just show you this. This get feature names out, and that shows it does still have all of those terms that we had in there. It just doesn't have them directly affiliated with the values like it did in the data frame, because it puts it in an array. This is one of the things that I want to work on, is doing some code where it'll change it, just leave it in the data frame and not mess with it. But a lot of the things in sklearn wind up putting stuff in NumPy arrays. And so you've got to do some other manipulation in order if you want it in a data frame. So I'm going to convert that into a data frame. So I'm going to call this this data frame temp. And so we call pd.dataframe, and data and frame are capitalized. And we're going to make a data frame out of that teens_standard. So the standardized data, there's an argument called columns. And so we set the columns equal to that stdsc dot get features out, get feature names out. Actually, maybe I should go back and do this way where I put everything on its own line. It's a little easier to see. So that's going to create a data frame and put the columns and the data back together. And then let's just take a quick look and see if that's going to work. And so that looks a little more familiar. Everybody okay? You'll see why the next cell is left in there.
Yeah, I was able to keep up. So it looks like, well, you know, you could write a function that you pass the
Yeah.
data, you pass the data frame and say, leave out these columns. I don't want to standardize, you know, give it a list of columns to not standardize, and then
Yeah.
do all of that stuff in its own, you know what I mean? In one line, you could do that in one line of code. And
Yeah, the other thing you can do, and we do this as a intro thing in my data mining class, is that you can just write a really easy Z function and just apply it to the columns that you want. So one of those two ways is where I'm going to go down the road. So, but this is the way that you use what's built into sklearn, which is kind of the standard out there. But it also depends on how close you are to the user end versus how close to the data science end. The data science, highly technical, they're going to want to do all this kind of stuff. So, like I say, it's one of the things that I'm hopefully we'll have time to work on. There's a few things like that where it could be streamlined a little bit for more of our business users.
And just 20-second aside here, Mike, for the group.
Yeah.
Things like the one hot encoding can be done. I know it can be done in Excel. I'm pretty sure you could do something like that in SQL. So it just depends on your data engineering environment and which tool you're using for which stage of the stuff as to how you implement these techniques. But the techniques themselves, the underlying reason for doing it and the effect on the model are universal.
Yeah, very much so. Yeah, use the tool that works the best. One of the downsides, and I tend to use Excel a lot myself, but one of the downsides of using Excel is that if this is data that you get regularly that you have to work on at work, you have to go in and manually do that every time. If you do it in code like here, then you just run the code on the new data and it does it. So it's a lot easier to replicate.
How many times have y'all heard me say that?
Or to repeat.
If it's a repetitive process, code it. Because
if it's one off, then yeah, just do it in Excel.
Because you're going to forget something or do something wrong or whatever if you're doing it manually in Excel or whatever every time. So yeah, automate everything you can, and that way it's repeatable. That's my.
And it's another one of those things that you have to learn on your own. So you have to hose yourself by not doing it that way and then go, oh gosh, okay, those old guys were right. So, well, no, you probably aren't going to admit that, but you're going to admit that it does make some sense to do it. And I'll tell you, I've done some of this, cleaning up some survey data for some research that I was doing with two of my colleagues. And it was like, well, we want to look at this different value. It's like, okay, I go in, here it is. I could run it in literally less than a minute. Whereas if I had to go back into Excel and do it, it would take me, you know, an hour or more to do it. And then when we said, well, okay, let's look at this version. So it just makes it a lot easier in a lot of cases, but by all means, use Excel wherever you can, if you can get away with it. If it's a one-off deal, then yeah, you can just do it there. But we'll see too, that even here, it's not real hard to do the one hot. So I'm assuming everybody's been able to create that temp data frame. So this next file or the next cell just puts grad year, gender, age, and that temp that we just created back together. Axis 1 says they're columns. Let me put that on another line. And then to take a look at it. So now it should look, now it looks the way that it did when we first started, basically, except that all the data is standardized. So like I say, it's kind of a pain doing it with this tool and trying to figure out, there's a possibility you might even create a package to do, but that's, you know, that's kind of long-term stuff. So if everybody is at this point, then we should be good. Does anybody need a second? I just saw there was something in chat and I was going to say, hey, pop in. And then I saw it was you, Don, putting some code in there. So that's good. Okay, so we've got the data looking the way that it was before, except that the data is standardized. So we just want to do the one hot encoding. There's a lot of different ways that we can do. We can save it as a temp and do all that stuff, but I like, when I'm working on this, to just save it in the same data frame, because I can always go back and rerun the code above here to if I screw it up, I can, you know, recreate it, and I don't have memory filled with all these different data sets. So I'm going to save this back in teens. I'm going to say PD pandas get underscore dummies. And if you just do get and underscore and a D, I think and tab, it'll come up. So what we do with get dummies is we tell it what's the data frame we're working on, and it's teens. And then what columns, so let's use this columns argument, and we can put in multiple columns, but we just want to do gender. And then remember, I was talking about how we have 3 values, but we only need 2. That's the whole degrees of freedom stuff, if you've heard of that before. And so I'm going to tell it drop first, and it will drop the first value. Drop first equals true. And it will drop that first value. And then I'm going to look at the header in order to see, but we do it in that one statement. So you'll see now we've got all this stuff that we had. We don't have gender up here anymore. Now we have gender M and gender U, so it dropped gender F. Why did it drop female? Alphabetical order, that's all. So we can actually, there's an argument where we can specify which one we want to drop. If there's a reason based on experience or theoretical conditions or anything, we can tell it to drop a specific value. So now we know that first row is male. The second row is female because it has zeros for male and unknown. And then we know that 5th row is unknown. So we've got our one hot encoding. We've got all these other values here, standardized, age, grad year. We're good to go. So we are fully prepared for our data analysis now. Anybody have a question or issue? Okay. So we're ready to create the model. So what K value? The author of the book where this paper comes from, this example, loves the movie The Breakfast Club. If you haven't seen it, it's from the 80s, and it's about 5 students that all get Saturday detention, and they are 5 stereotypes: a brain, an athlete, a basket case, a princess, and a criminal. That's what they're called. And so he says, we're looking at sociologically categorizing teenagers, so why not use that? Like I said before, getting a model that you can use is often much more important than trying to figure out what the exact best K is. So we're going to use K equals 5. We're also going to see a random state value in here, and the random state makes anything that we're doing with random numbers start at the same place so that we'll all get the same results. And then if we were going to use this out and deploying it, or we're doing a different analysis, we wouldn't want to set that. We want to let that vary. But for our purposes now, we'll set random state. And the other thing is, I told you, we wanted to run the model using just those feature words, those 36 feature words: basketball, death, shopping, all that stuff. So that's the thing I'm doing here, is creating this teen model data frame, dropping graduation year, age, friends, and the gender, male and unknown columns. So it just has those 36 feature words. So this is what we've been building to, is to create the model. So the first thing that we do is create the k-means object. So we're going to create k-means, and that equals capital K, capital M means the function that we imported in our library. And there's a bunch of different options. In fact, we probably should have taken a quick look at that, but we'll do that on another technique. But one of the main options is n clusters, and we're going to set that to 5. Like I said, that's our K value, number of clusters. And then we're going to set the random state value, and we'll just set that to 101. So the actual value doesn't matter that much. We just want to all have the same value. Now that creates the k-means object. We create the actual model, which we are going to cleverly call model, by taking that k-means object, so k-means dot, and we run a fit method that's built into that. And we run that on the data that's in teen model. Now this is the same process that we follow with just about every technique. So you're gonna see this multiple times. Now there's nothing output there. So if we run that, I have no errors, so I should be okay.
And
If you have an error, then you probably have a typo in there.
what is teen model?
That's the data that I just did up in this cell before, where I dropped
data frame. Yep.
Yeah.
Okay.
Yeah, it's just that data frame that has just the 36 columns in there. Now we could easily do a subset in here and lots of other stuff, but that's ready to go. And then let's see what it actually predicted. Now we could just say model dot labels, and labels has an underscore at the end of it, and it'll show what we have. But actually what I want to do is I want to create an object called labels to hold that, and then print labels, and you'll see why here in just a minute. It's the same output, but that just shows the labels. So it predicted that they would be in class 0 through 4, because it's going to be 0 based. So it shows those are the clusters that it's going to be in. Now that doesn't mean much when we just look at those like that. So let's take a look at, first of all, are those good clusters? Well, we don't know, because like we said, it's unsupervised, so we don't have anything to test it against.
Hey,
Silhouette coefficient. Yeah.
I missed that when you mentioned the underscore at the end of labels. That's odd. I'm not used to seeing a method or anything that ends with an underscore like that.
Yeah, there's more. If you get more into a lot of the details of the programming, they have that, but that's the way that this attribute, the way that you access it, has labels underscore.
It's just a naming convention then, right? It's not
just, yeah,
an
yeah.
operator or any.
It's
Okay.
just, yeah, there's also some conventions where things start with underscores, but we're not going to get into that. But yeah, there's a couple of places in here where we use an underscore at the end. It could have just as easily been an X or something, you know.
Yeah, it looks unfinished is what I'm
I
wondering.
know. I
But if
know.
I-
It's one of those things you have to get used to.
I should have written scikit-learn if I wanted to name the syntax, right?
Yeah. Well, yeah, and scikit-learn, like I said, it defaults to NumPy arrays and a lot of stuff, and so it was written by some really technical people that really want to get into the computer science and math and stats and stuff. So that's why a lot of these are there, because you get into CS, there's a lot of underscores used that you wouldn't normally see in a more casual programming environment. So
There you go.
that's what you got. So I mentioned silhouette coefficients before. We'll talk about those. It gives you a measure of cluster quality, but you can't know for sure because we don't have anything to combine it with. The other thing is just printing out the labels here like this doesn't mean a whole heck of a lot. So we're going to take a look at what I like to do is add those labels as a new column to the original data frame so that we can check it out. So that's another reason why I created teens model is so that I wouldn't mess with the original teens data frame. And I'm sure you guys have done this. We're going to add a new column. So we just give it a name that's not already there. So I'm going to call it cluster. So teens cluster, and that's going to equal labels. And then let's look at 15 rows at the top. So we see all of our data here, and then our last column is cluster, and we could easily put that at the beginning and do a bunch of other stuff. But so we see that there's a lot of them here at the top anyway that are in cluster 0. There's 2 and 3 and 4 and all that, a lot of them in 0. So maybe what we want to do is take a look at how big are the clusters. So we can do what we've actually already done before is use this cluster.value counts. And we see the size of the cluster. Now, one of the things that's really annoying about this, I think, is it puts it in descending order of the value counts. So if we add to the end here, sort index, now it gives us the values in an order that means a little bit more, I think. So you see there's so many zeros in that first bunch because we had over 21,000 that got clustered together in cluster 0. We only have 872 in cluster 4, 600 in cluster 1. So let's take a look at, I'm going to talk about this again here in just a second, but let's take a look real quick at the silhouette score. So we remember we imported metrics. So we use metrics dot silhouette, and silhouette has an H after the L. That's, to me, is very hard to remember. So you see silhouette score. And what we do, and this is with all the metrics that we do, we give it the, well, actually, I'm kind of getting ahead of myself, but in this case, we tell it what's the data, teens, and then the labels. And then we get a value. What this is doing is it's looking at the average distance between points inside a cluster and the average distance between points to the nearest cluster. So there's a lot of calculation going on there. So you see we get a value of 0.295. As I said, the best score is 1 and the worst is -1. If it's around 0, then it shows there's some overlapping. So there's some overlap here, but they're not horrible. But remember, with clusters, we have no idea if these are really good or not, because we have nothing to compare it to. So it looks like from a silhouette score, it's not horrible. We can take a look at some other things with these clusters to see if they make any sense. So we can look at teens.group by, and that's a parenthesis, and we'll look at clusters. So we'll look at them grouped by cluster, and then square brackets age dot mean. So let's see what the average or the mean age is in each of these clusters. Because if we had all the 18-year-olds in one and all the 13-year-olds in another, then something might be going on there that just has to do with age. But these all look pretty, they're within like 6 months of each other, a 6-month range overall. So they're actually distributed pretty good. If we look at just cluster 0, we'll see that it's about 70% female. So let's take a quick look at that. So teens, we're subsetting teens cluster. So let's get all of the rows where cluster is equal to 0. And then I'm actually going to add describe and .t on the end. So you see, this is the describe function run on just cluster 0. So the mean age is what we were expecting. We can look at some of the values. So this is, if we're wanting to do something with these clusters, then we can look at all this kind of stuff. So if we find out that this cluster is really high in, say, basketball, football, and soccer, then maybe these are the athletes. Now, that doesn't mean just because those are the categories that we were thinking about going on that we have an athlete category, but just thinking that there's 5 stereotypes means let's look at 5 clusters. Now, we could also go in and rerun this with 7 clusters or 4 clusters or whatever and see if our silhouette score goes up and we get better clusters. It just depends. Like I said, if we were going to run a certain number of marketing campaigns, and we knew that we could do 4 of them, then we'd run 4 clusters and do the best we could with that. So clustering is really interesting because we can group different data together, but we never know just how good this grouping is until we start trying to use it. We can get an idea with silhouette score and a couple other things. I mentioned the elbow method. What we would do there is we can run multiple models and get something like a silhouette score and then plot it. And on the plot, if there's a place where it bends, either coming down and bending, depending on which way we go, if there's a big bend in the plot, then that's going to be the best place because of the bend. It means there's not much value after that. So it could turn out that maybe 6 clusters or 9 clusters is the best with this.
Mike, not to get ahead of you or distract, but I'm trying to think of the kind of the practical application of this. So we created these clusters based purely on the frequency of keywords that they use, the most popular keywords. We didn't look at we didn't cluster them by age or sex or grad year or anything like that. Nope. Just the keywords. So is there a way to extract, and I'm thinking like if you were, a political science researcher and you were trying to cluster voters or, different types of customers for your business or whatever, how would you extract the more meaningful demographic stuff in a given cluster so that you could typify these are, white men over the age of 40 that are all into woodworking or whatever the case may be, you know what I mean?
And that's kind of what I'm doing down here at the bottom is just taking a look at those. You can subset those different clusters and then look at the different data, because I think this was the one I was looking at before. See, if we look at this was the max value out here to the right, so the min and the max. So the max value in this cluster on die and death and drunk and drugs, some of the more negative connotations, are pretty high. But if we look at the quartiles, they're all the same number. So those may be more outliers. So that doesn't mean that it's necessarily indicative of what the whole cluster is like. Now, I said that this was at least 70% female because you see our mean on male is 20% essentially, because it's 0 or 1, right? And then the unknown is another 10%. So it's going to be at least 70%. And then it could be higher than that if we had some of the unknowns straightened out. But we can look at some of these different values and see where they're, the different values are maybe higher than other clusters. So we can continue with a subsetting, and by graphing and just comparing some of this, we can get to some of what you're talking about.
Okay.
And that's like I said, that's the reason why leaving grad year and age and friends in here, because if you just clustered by that, then you'd have everybody that's the same age and would be in the same graduate year. And then all of the people with lots of friends would be in a group, and all the people with no friends would be in a group, and there'd be some in the middle. And so there's not a whole lot of help there. But by taking care of all that stuff in the prep stages, then you can continue this analysis to go on and try to make some kind of applicable meaning out of these clusters.
All right. Are we at a logical break point?
I think so.
Okay.
Yeah, because we'll do k-nearest neighbors next.
All right. Well, let's take a quick one. Reconvene in 10:35.
Okay.
All right. Welcome back. Third hour,
Okay.
Machine learning with Python.
Okay. So I mentioned I want to talk about k-nearest neighbors, and we're going to talk about the distance calculation that was used in k-means and is used here in a little more detail, and then go through this example. And then those last couple of examples will go pretty quickly, but we'll have all the basics done here. So I mentioned that it's supervised learning, and remember that means we have a target. We're trying to predict something specific. So instead of creating a cluster, some sort of a association between the data, we have one in mind that we want to see which one of these does it fit into. So this is often considered the most frequently used data mining method. Partly that depends on linear regression, if you include that in that list or not. But between just some basic classification like we're going to do in linear regression, those are used more often than anything else. We want to get all goo-goo-eyed about neural nets and all this fancy stuff, but this stuff gets the job done most of the time. So we use the supervised learning. That means that we have to have some data that has a result associated with it, and then we use that to figure out what's the relationship that explains that group membership, and then we use that to predict it on a new set of data. Why am I not? There we go. So the output value is categorical. It's going to be yes, no, true, false, male, female, unknown, small, medium, extra large, large. It's going to be something like that. So we call that the label. And so we'll talk about data that's labeled, that has that, and unlabeled data. So there's binary, the yes, no, true, false, male, female kind of stuff, multi-class. And in k-nearest neighbors, we go right to the output class, but there are other methods like naive Bayes that we're not doing today that calculate probabilities first and then make a decision based on that. So we're not going to do that. You can get probabilities in a lot of the techniques. I'm not going to bother with that today either, but it tells you how sure the method is of its prediction, but you have to remember that it can be very sure of a wrong prediction. So you have to use it in a type of in the context. So keep in mind that in a lot of classes and things that you take, you're just kind of expected to know basic data like names and dates or terms and definitions. But in other situations, you take what you learned and then apply it. And that is really what we're trying to do here with the classification. Is we're trying to generalize. Remember, we talked about the generalization is take that experience and then generalize it to new situations. So we talk about unseen data, that the model has not seen the data yet. That just means that it had nothing to do with the way that the data was created, or the model was created. But it does imply that we have to have unseen data where we know what the true result is. So if we're doing a credit analysis and we're wanting to decide if a potential customer is a good credit risk or bad credit risk, that means we have to have data on customers that turned out to be good or bad credit risks. But we also have to have unseen data that we know they're good or bad, so that we can make a prediction on that data and then compare to the true results. So there's different ways we can do that. We can have separate pieces of data, but if we have one big data set, we can split it into two parts. We call those two parts the training data. That's what we use to create the model. And the testing data, we use that to evaluate the model results. So that's one of the things that we're going to do, is split our data into training and testing data. If we don't have any unseen data, like if we just ran a model on our total data set, all we'd be doing is describing the data. It looks like these relationships are there and that, but we can't see, will it work? Will it generalize to other data? And usually when we're doing this, that's what we want to do, is generalize it. So the most basic way that we evaluate the model is to look at accuracy. And it's just like if you're taking a multiple choice exam. So the number correct over the total number of corrections, or total number of questions. So it's the number of predictions you got right over the total number of predictions. And it's built in that we can do this pretty easily. So let's say we have 1,000 examples. We create a model to predict credit worthiness. What are the classes that we're going to be predicting there? Well, it's going to be yes and no, or good credit, bad credit, however it is that you want to, or it could be true, let's loan them money, and false, let's not loan them money. However you define it, it's going to be those classes. So if we test with 100 examples and we got 90 correct predictions, what's the accuracy? And I'm actually asking this, somebody answer and don't overthink it. I can hear you all overthinking this.
Jeanette, I'm going to pick on you because I can see your name on my screen.
So if we got 90 out of 100 right, what's our accuracy?
I saw you come off.
Would be
mute.
90% accurate.
90%, yeah.
Again,
Don't overthink
again,
it.
overthinking it.
We're not alone, Mike.
Yeah, we picked I picked the numbers to make it easy, but yeah, I know my students overthink stuff all the time. They think there's got to be more to it than that. Like, no, it's that simple. Just how many we actually got right, because we can take that test data that we have actual values. We know that these 100 examples, we know whether they were good or bad credit. And so we can make a prediction and then compare it. So that's the most basic thing that we're going to do in order to look at accuracy. So with k-nearest neighbors, we're really trying to find the things that are most alike. So the idea there is that things that are alike usually have properties or attributes that are also alike. One of the examples I've seen before is, think about going into a school and looking, you got different groups of kids sitting together, and the people that they're closest to in the cafeteria usually have attributes that are like them. And that's the kind of thing we're looking at, is we look at the K closest items and we compare how those things are labeled and then apply that label to an unlabeled point. So if most of the customers that are similar to this other customer or potential customer are good credit risks, then they're probably a good credit risk too. It's really that simple. Now we'll go into some other, show you some other details of it here in a little bit. But k-nearest neighbors is called a lazy learner. And it's a lazy learner because there's no abstraction step. I just spent some time a little while ago talking about how that's one of the steps in machine learning. But k-nearest neighbors doesn't do that. If you're going to use a k-nearest neighbors model to try to classify some data that you don't have, you have unseen data, it runs this stuff every time. It doesn't create an abstract model, even like we did on the clustering, where we had a model we could apply, and we'll see with decision trees and other techniques that it creates a model that we can apply. So it's not real efficient, It does all the calculations every time of all the distance. So it really isn't learning anything, but it's used so much because it is just so good because of that whole idea that items that are similar have similar attributes. So let's do it. It might even change a little bit over time as you learn more about data, but you can find those natural patterns that don't jump out at you pretty easily. And even with a lot of data, it doesn't take forever, but it can take some time to run. So I mentioned about distance and similarity, and I've got several slides here, and I don't want to go too deep in them unless somebody wants me to talk a little bit more about this. But the idea here is we find points in space, and like here with 2 dimensions, we can get the distance between A and B by taking the difference between the X coordinates and the difference between the Y coordinates. We square each of them so that we get rid of the negatives, add them together, take the square root, and we call that the distance. That's Euclidean distance. Now here too, I've seen like 4 other distance calculations. One of them is called Manhattan distance, and Manhattan distance would actually follow this dotted line. It's just like getting around in Manhattan, where you can't go diagonally through most buildings. You have to go down a street and then over. That's Manhattan distance. There's others, and they are used in different situations, but just general Euclidean distance works most of the time for you, and it's a little easier. So I've got some examples here calculating the distance. Like I said, we have person A and person B in 2 different features. So we just take the difference. We call one feature X and one Y, and we take the difference between those values. And so we can find the distance between those 2 points. So here's person A at 2 years at the residence and 2 years or 2 of residential status. And then B over here, 10 years at residence and 1, and we get the distance between them. So if you calculate it, it comes out to about 8.06. If we've got multiple features, we do the exact same thing. It's just that we have more terms now. So we subtract, so 23 minus 40, we're getting the difference between person A and person B. 23 minus 40, square that, plus 2 minus 10, square that, plus 2 minus 1, square that, add them up, square root. So distance is 18.8. So about 19. Now, keep in mind that distance means absolutely nothing by itself, because there's no, what kind of units would you have on that? It's just the distance is 19. But 19 is further away than 12, and it's closer than 31. So we can compare it in the same data set, but we can't go to a different data set and say, oh, well, this data is a lot closer because the distances are only 8. It's like, no, that's totally meaningless. But that's how it's calculated. And then we can use those calculated distances to find the nearest neighbors. So we talk about the K value. We look at, say, 5 nearest neighbors. Let's calculate all the distances between all the points, and then find the distances that are the 5 closest, and then see how those are labeled.
Does that obviate the need to standardize the scaling because it's doing the distance on the same
No,
feature each time?
I'll show you here in just a second.
Oh, no.
Now I've used odd numbers for K most of the time. We use typically majority voting. So if we had used 6, we could have 3 and 3, and the algorithms have ways to work that out, but it might not be the way that you want. So we tend to use odd numbers so that we don't get ties. I've got an example here. Again, I'm not going to spend too much time on this, but you'll see if we're looking at, will David respond to a credit card offer? And we're going to use K equals 3 here. And so we have David is our unlabeled data, that first row. And then the other stuff is labeled because we have a response variable there, yes and no. So that's going to be our labeled training data. So what we do is we calculate the difference between David and each of those other customers. So if you look at the numbers for John, we have the age, 37, 35 difference, 50 and 35, 3 and 2, square it, square root, and we get 15.165. K was 3, so let's look at the 3 closest neighbors, and then what was their What was their response? Yes, no, and yes. So that would be 2 yeses. So we would predict that yes, David will likely respond to our offer. But as I said, they're still on very different scales. So income is made a little bit better by making it in thousands. So this 50 is 50,000. And you'll see that a lot in data when there's bigger numbers like that. It'll be in thousands or millions or something, but it's still on very different scales. So we still need to rescale the data. Otherwise, like age, we have like 63 and 200 here versus 1 card. They're going to have a much bigger impact. The age and income will have a much bigger impact than the number of credit cards that they already have. And if we're sending out a credit card offer, that might be the most important feature actually that we know from experience. So we still have to standardize, we still have to rescale. In fact, the decision tree is the only one we're going to talk about where we're not going to do that. But in almost every situation, we rescale the numeric variables. Like I said, if they're all on a 1 to 10 scale or something, then we're good. If they're on the same scale, you don't have to worry about it. But even if you did it, it would change the numbers, but it wouldn't change the model. But you still want to do it. It'll throw off the results otherwise. Of course, this is where I was talking more about this feature scale. I thought I was doing this earlier. So there's a min-max fixed scaling where you just put it on a 0 to 1 scale. You use that in neural nets and optimization, but this one can be really sensitive to outliers more so than standardizing. So we use that in neural nets and other problems, but our default is to standardize the way we've done already with the z-scores, where we put on a scale where the center, the mean of each feature is at 0, and then we do the standard deviation. So they tend to run between -3 and +3, but we can have them above that. I've also mentioned that we're going to split the data to have that labeled data to test the accuracy. And I've already talked about that. So we're going to split the data set into the training and testing parts. And so here's an example of what, and I think it sounds pretty intuitive up front, but I've found that as we've gotten into it, the students have a hard time picturing this. So this is actually the data we're going to use in the linear regression later. So the first thing we need to do is split out, if we have it all in the same data frame, is split the target and the feature columns. So all the features, these are all the feature columns, and whoops, wrong way. And then target, the MPG is target. We're going to find in that linear regression, we're going to try to predict the MPG value, the miles per gallon, from all these other features. So those are the target and the features. So we need to separate those, but then we also need to separate training and testing data. Now we do that randomly, and in this example, when we do it randomly, these are the splits that we get out of the first 10 rows. So we wind up with 4 data sets. We'll wind up with training features, testing features, training target, and testing target. So we'll see that in the code. But like I said, you see it in the code and everything, but you kind of have to understand this is all coming out of that one data set that we had, so that we're able to use this to use the training stuff for creating a model, and then the testing data to evaluate. We're going to use this train test split function. There are a couple of options here. We can set the test size. It's personal preference in a lot of cases. Tends to be 10 to 30%. Different people say that it should be typically different values. I tend to be around 20%, but it depends also on the size of your data. The more training data you have, usually the better model you get, because the model's based on more data underlying it. So if you have 1 million rows, then your testing data set doesn't have to be 20%. It doesn't have to be 200,000 rows. It can be 50,000. So it can be a much smaller percentage. But you have to look at the different trade-offs there. We're using random state again, just like we did in that last one. And so I've got the same note that we're not going to use that later. Now, we're going to scale the features like we talked about, but we're also splitting all that stuff. So is there a difference between standardizing it and then doing that train test split? Or should we split and then standardize? There actually is a little bit of a difference, but we want to split it first and then standardize, because we want to standardize the training data and then use the same values we use to standardize on the test data. It can be kind of a subtle difference, but the issue is that if we include the test data when we standardize, we've now used that test data. It's influenced how we've built our model, and that's called data leakage, and that's not good. So we want to standardize the training data and then use the same parameters to standardize our testing data. And we'll see we'll see how to do that in code. It's not a big deal, but you need to understand why we're doing that. And it could be that if we're splitting those randomly, what if we randomly got all of the really big values in the testing data and we didn't have them in the training data? So they're actually, even though we standardize them, they're going to be on a different scale. So we need to standardize on training, make sure it's all on the same scale as the training data. If we do things randomly, and a couple things I'll talk about at the end of our time today, it's not a huge issue, but we do want to split first, then standardize. Talked about accuracy. We're going to use this accuracy score in metrics, and then I'm going to have you a little shortcut on something else earlier or later in an example. So we're going to talk more about hyperparameters here later, but K is called a hyperparameter. Parameters can be impacted like the number of or like the cluster numbers and things that were inside our clustering results. But hyperparameters are set before you start running your model. So in order to change it, you have to run a new model. So we'll see that with K nearest neighbors too, is K is a hyperparameter. So we can do it with K equals 5. If we want to do it with a different K value, we run a new model. We don't see anything adjust inside there. And I'll come back and talk about that a little bit more later on. So I'm going to switch over to the code. If anybody had any questions or comments about any of that, then this would be a good time. Otherwise, there it is. Otherwise, I'll go over to my notebook. So we're going to follow this same general process. And I mentioned before the same standard library calls we did before, except that we add this model selection library call because that's where we use the do the train test split. I mentioned we've got these different model selection. Here's all the different things that are in here. We're going to use, let's see, where is it going? You can see all these different splitter functions. We're going to use train test split here. So, but there's a lot of different other things. We talk about hyperparameter optimizers and stuff later. And then metrics is another place where there's all kinds of ways. Here's all the classification metrics. We're going to talk about accuracy score, and we're going to talk about the classification report, and we're going to talk about confusion matrix. But you can see all these other things that you can do. So there's lots and lots of things in here. And regression metrics, we're going to use one of these. So lots of different things that those help sites are just really a wealth of knowledge about all this stuff. So I'm going to load those, the libraries that we need. And I think this is the last time that we'll actually type that stuff in, but I'm doing it now at the top of the notebook, the way that I would want to do that. So I'm going to, almost as always, import pandas as PD. And then I'm going to do that same sklearn.preprocessing. From that, let's import standard scalar. Remember, we've got to capitalize. And then I'm going to add this from sklearn, import model selection, model underscore selection. And then one of the standard conventions is that we go ahead and give this an alias. We call that skms, and that's why you saw that on a slide. So sklearn model selection. That just allows us to use a little shorter in our code. We're also going to, from sklearn, import neighbors. And then we're also going to, from sklearn, import metrics that we did before. So it's the same things as before, pandas, the pre-processing. We're adding this model selection skms, and then we have our specific part of the library that has our specific modeling technique, which in this case is neighbors, and then our metrics. So I need to run that before I forget and move on. So we're going to use this Wisconsin breast cancer data, which is going to predict benign and malignant. And we'll see that here in just a second. So let me go ahead and load this up. So I'm going to save it in the data frame WISC for Wisconsin, pd.read CSV. And that's going to be in the data folder if you're sticking with the what you have. So it's WISC underscore BC underscore data.csv. And then we are going to, like the question came up from Don before, this has an ID column. And so we're going to use index underscore column equals ID, so that we make that the row index, and that'll get it out of the way. Now, for the purposes of creating our model, we could just read it and then drop that column and get rid of it because we don't need it for the model. You would need it if you were going to use this data with a model to make a prediction, because you want to go back and identify each individual example in there and the person connected to it if you were going to give them a diagnosis. But in this case, we don't really, you know, it sounds heartless, but we don't care about the individuals. We're looking at all the data to create the model, right? So we don't necessarily have to have it identifying the rows, but it works fine like this. Everybody good to that point? So we'll see that what we have here is we have diagnosis. That's going to be our target. So that's going to be, that's the only object. Everything else is a number. So we're good there. We have 1 through 30. So we have 30 different measurements here. And if you look at them, you'll see that there are actually 10 measurements, and we just have, like we have radius mean, radius SE, which is standard error, and radius worst. So it's 10 measurements. It's the mean, the standard error, and the worst of each of those. So we have 3 times on each measurement on different types, different tumors. Yeah, unfortunately, a lot of the data mining stuff, sometimes you're looking at stuff that's not real happy, right? We're looking at breast cancer data here, and I've looked at worse than that. So, but a lot of times that's what we're using machine learning for, is to help us make good decisions. In this case, a good diagnosis of breast cancer, whether it's benign or malignant. And we'll see if we do head on the WISC data frame. So you'll see we have the IDs are in our row index. The diagnosis is a B for benign and M for malignant. I have to keep reminding myself that benign is not cancerous and malignant is cancerous. So if you're a doctor working in this stuff, you would just know, you wouldn't have to think about that. And you see all of the values. And you can also see here too that, like radius mean and area mean right away, and smoothness mean, there's 3 completely different scales. So we're obviously going to have to rescale, and all the way through to some really tiny stuff over here. So let's take a look real quick at what are the values of diagnosis? So let's use that value count again, or value counts. I'm trying to use the autocomplete and my computer is very slow. So you see we have 357 benign and 212 malignant. So they're not 50-50, but not horrible. So I want to look at the first 10 rows here, and let's do WISC dot sort in underscore index dot head. And the reason is I'm going to show you the results of when we split this, just like I did on the slides of the train test and the other stuff is we'll show you the results. And so we've got to sort it by index in order for that to come out right. I'm not hearing any screams or anything, so I'm assuming that we're in good shape.
I'll unmute next time I scream out loud.
So, okay, fair enough. So we're using, that's going to be our reference when we look at how these things get split up. So the data is clean. There's no general data cleansing stuff that we need to do. There's no missing or any of that kind of stuff. So we're okay. So we're going to look at some of the specific data stuff we need to use for the model building because the general stuff is okay. So there's no categorical features, so we don't have to worry about one-hot encoding here. But we do need to split the data. So what we're going to do is first separate the target and features in the data frame. And I told you one of the things we're doing is kind of building some standard code that you can reuse. So one of the things I want to do is let's create an object called target, and we'll create another one called features. And so we'll be able to do stuff with that. So target is just going to be the diagnosis column. Features is going to be what? It's going to be everything but the diagnosis column. So it'll be the Wisconsin data frame, WISC, and let's drop. And we can do this other ways, but I like using this columns keyword now because it's a little more self-documenting. So we're now, keep in mind, we're not changing the WISC data frame. We're just saying create target that just has the diagnosis column and features that has everything but the diagnosis column. So that's our first split. Then we want to split both the target and features into train and test sets. So this whole process takes 2 lines of code here. I talked about all this and everything. So let's just do this. I'll come back, put TTS equals, and we'll talk about what that is here in just a second. So we're going to call SKMS. Remember, we had that in the library call. And we're going to use the train underscore test underscore split function that's in there. And it has several arguments, but there's really just 3 that we want to put in there. The first one is, what's the data that we want to do this on? And it's everything that's in features. Remember, target is going to is a B or an M, so it's going to be we're gonna split it in just a little bit, but we're going to do this based on features. So like I said, we're going to do the split, and then we're going to standardize later if we need to. So we put features is the first one that it's going to be based on, and then target is the other set of data that we're also going to do it on. And then I mentioned that we have a test size. So we tell it, how big is the test data going to be? And I'm going to put 0.2 for 20%. And then we have a random state again. And let's make that 101. And again, the value itself, it's important now that we all have the same value, but other than that, we get different values because it splits it differently, but that's it. So what this is going to do is it's going to take the the features and the target, and it's going to split both of them into 20% test and 80% training data. And then it's going to save them in this object called TTS for train, test, split. What it does is it saves them as 4 different parts. So in this next line of code here on my line 12, we're going to take those 4 different parts and save them as 4 different data sets. I don't know if you guys have run into this, but one of the neat features about Python is that if you have something that returns multiple values, you can put multiple variables on the left side of an equals, and it will put them in those different variables. And this returns 4 parts. So we're going to create those 4 parts. So we're going to call them train features. Did you have?
I just want to be really clear. The target is a series,
right?
And features is a data frame without that column, without that series.
Right.
And when we do the split, it keeps the diagnosis with its corresponding row in the other data frame, right?
Yeah, it'll keep
it doesn't
together.
randomize both of them independently.
No, because they all have the same index number.
There you go. Yep.
Remember that the data frame is actually made of series that are columns that all have the same index number.
Yep.
And so because target and features have the same row index number, in this case, it was that ID number, but it could be 0, 1, 2, 3, 4. But yeah, so it keeps it associated.
There you go.
So the first one that we get is train features. The second one is test features. So it splits features first, and then we get train target and test target. So those 2 lines, line 8, 9, and 12, actually split our data and then create 4 data sets that come out of there, like I was showing on the slides. So we have our training features, our testing features, our training target, our test target, in that order. But this is very much code that, other than the test size and random state, you can just use like this and don't change it. And then we'll just use train features, test those different objects in our modeling. But the first thing I want to do is let's do train features dot sort index.
Are you not running that previous block?
Oh yeah,
on purpose?
No, I just moved on.
Oop.
So there, I ran it. It took less than a second.
I
would have had an
crossing
error
my
here.
fingers that I typed it in right. How about that? That's a lot of code. I usually go line by line by line.
And we're not going to type that again, but I wanted to do it one time. But here's what I want to see in these next. We're just going to take a look at the different parts that came out of this. So, so we'll see if we sort it. These are the training features. If I go back up, and in fact, I'm assuming that everybody's getting this here. If they don't have it already, they're getting it in a few seconds. So I have IDs of 86, 70, 89, 13, 15. So if I go back up here as a reference, you'll see 9047 is not there. So it's not part of the training. And one of these other ones down here, it might be 355 or 409, I don't know, is not there. So the top, these are the top 10 by ID order. And so if we look at the top 10, how they were split out, there's 355, 408 and 409 are both not there. So, okay, 47's there, 408, 409 is not there. So it's done randomly, starting on using that random state. The testing features, we can look at test underscore features dot sort index dot head 2. So you see, those are the first 2. There's the test features. Something got messed up here. $87, 163, and something got messed up in my sorting. Well, anyway, it'll show you that as we look at it, that those different values. Let me see if I can go a little bit longer on this. I won't skip over it now. Okay, well, my sorting got messed up. This the idea here was to look at all these different things and see how they came out of those first 10 the first 10 items. So I don't know how that it could be that it just, you know, it's doing it randomly. It might not have picked them out of the first 10, but I'd done this before and it came out fine. But now I'm seeing in my notes that I had the same issue, so I should have fixed that before. So my apologies for that. So I was you check the training and testing, and so you can take a look at that if you want to, but we're gonna cruise past that right now. But so we've got, anyway, those 4 different data sets. So we've got training features, testing features, training target, testing target. So now we're going to standardize it. And like I said, we could do this actually pretty easily. We're going to do the same thing we did before. STDSC equals that standard scalar and with parentheses. So we're going to create that standard scalar object, and then we're going to get, we don't need to standardize the target. We just need to do the training and testing. So we do train underscore, whoops, standard is going to equal that STDSC dot, and we call fit and transform, which we did before on the train features data. And then we do test STD is going to be made from that STDSC dot. And here is where the difference is. Instead of fit transform, we just use this transform method that's built in on test underscore features. And I'll talk about that here in just a second. So that runs with no problems. So what this does, fit transform, the fit part actually implies it takes train features and it fits it in order to come up with a standardization scale. So it uses the mean and standard deviation of the train features in order to come up with the way it's going to standardize, and then it applies it using the transform. So when we use that same STDSC object and just the transform method, we're using those same the same results from the fit part from the training data in order to transform the test data. So that whole thing I was talking about of let's do this after we split, that's all we have to do is call fit transform on the training data and call transform on test features on the test data. And so that puts the test data on the same scale as the training data. So it's almost a little bit of a letdown. We talk about all that stuff and then it's just one little difference there. So we can also look at, did we actually standardize those? And then, yeah, there's the training data. So we're not going to look at all the different pieces of that, but there's training and there's and test. And so we can see that, yeah, those are standardized. Everybody okay?
So far, so good.
Okay.
Anybody need to slow down? Anybody get an error they want to correct?
Now, if this sounds confusing and stuff, I get it. But here's the thing. This too is code that we can use and we don't have to keep typing all the time. So this is one of those, we're inventing the wheel here and then we're good after this. We can just slap wheels on whatever wagon we do. So we're going to create the model now. We're ready to create the model, and we're going to use this same common structure that we did before that we're going to use on all these other techniques. So we create the model object, and then we fit it, and then we use it to predict. We did not predict with the clusters before, but we're going to this time. So in this case, what we're going to do is we're going to create an object called KNN. That is creating the model object. And so there we use that neighbors that we imported, and it's capital K, capital N neighbors classifier. You see, there's a K nearest neighbors regressor and a transformer. We want the classifier. And this has a number of neighbors argument, and we're going to use 5 here. So that creates the model object. Then we use that model object and we fit it to the training data. So we're going to have a result called model. That'll be our the model that we're going to use. We call that object, and we call the fit again, and we use train underscore standard and train underscore target. So that says use the data in train standard, and what we're trying to predict is train target. So that's where we're going to try to figure out where the relationship is between that training data and the target that we have there. And then we can use that model to make predictions, and we're going to call that preds for predictions. And so we use model dot predict, and we're going to do it on the test data. So in that one cell, we created a K nearest neighbors object, but all we've done is that's like the setup. And then when we run fit on the training data and the training target, that's where we're creating our model. And then we're going to apply that model to predict from the test data. And so in preds now, we'll have some predicted values for the test data. But remember, we also know what the true values are on the test data. And so we can compare those in order to do an evaluation. So what did the model predict? Well, we can look at preds here, and it predicts, here it predicted B or M because that's what we're predicting. Now, how accurate is that? We can do that in the evaluation stuff. And since we're close to a break, I honestly thought we were probably going to be wrapping up about now, so taking longer than expected. But let's do a simple accuracy, and then we can take another break, and then I can finish up. So just to do a simple accuracy, we'll call out of that metrics that we imported. Remember, we were going to use that accuracy score function. And what we do, and whenever we're testing any accuracy stuff, we do it in the same order every time. First, we put the true value, which is going to be test target. That's the true value we know. And then we have the predicted value, which is preds. And so we'll see if this model is actually over 96% accurate. If you don't like that long number, and I do this a lot, add the round to the end of it. You can round it off to however many decimals you want.
So all that's doing is going through and comparing predicted to actual B's and M's.
It's
and
doing
giving you
that
a percentage of
it's doing
ones
that
it got right.
multiple choice test score, basically. Yeah, how many did we predict and how many did we get right? So we'll look at a little bit more about where that is, but that's kind of this next section. I've got some other slides to go over, but I may wind up skipping through some of this stuff a little bit quicker. But anyway, so this will be a good time, I think, for a break, and then we'll come back.
Okay, 11:26. So
I'll try to wrap things up. Okay.
11:35.
All right.
All right.
Thank you.
Okay, welcome back. Fourth final hour of machine learning with Python.
Well, you might have hit that final hour part a little harder than you meant to, but I get
That's
that.
Freudian.
I got to tell you, I honestly thought that I'd be done by now. So I was concerned about getting 3 hours. So I will tell you, but don't panic. I think I could easily go another hour and a half or 2 hours. But here's what we'll do is I want to talk about this stuff a little bit more. And then these last couple of examples, I will just go with my completed notebooks and we won't type any code and we'll talk about what it's doing. And then I'll just, I was going to pass along the completed notebooks to you anyway, Don. So we'll do that. We'll hit some concepts, go through some models, and so we'll go a little faster, but that'll be okay. Cause we covered, by the time we get done with this, we'll have covered most of the really important stuff that I thought we needed to cover. So we'll be good. So we'll definitely get done here in our final hour.
Okay.
So remember, we talked about that. We talked about accuracy. So there's other stuff that we can do. And one of the things that you don't always think about till you run into a situation is that the best performance measure captures whether it's successful at its intended purpose. So what is your intended purpose? If you're trying to predict a genetic defect in 10 out of 100,000 babies, if you just always predict that there's no defect, you'll be 99.99% accurate and pat yourself on the back and say, what an awesome model I have. But you completely missed the point of finding those 10 babies with the problem. So you have to make sure that there's an issue. In a case like that, it's a class imbalance problem. And we have that a lot in medical stuff because a lot of times we're looking at some horrible, unfortunately, disease or issue that is relatively rare. But if you're going to create a model to find that, just like if you're going to create a model to find fraud, if fraud is not that common, then you've got to take that into account. And there's some things we can do, which we're not going to do here. But sometimes when you're looking at this, where the model's wrong is more important than how many times it's wrong. And so that's where the confusion matrix comes in. And that's a really common way of looking at how good a model is, because it tells you what it gets right and what it gets wrong. So in this model, we call the class of interest what it is we're trying to find. We call it the positive result, excuse me. But there's no judgment about it being good or bad. So like in our breast cancer data, we would consider malignant, the cancer condition, to be the positive result because it's what we're trying to detect. That's very common too in medical conditions. Or if you're looking at fraud, the positive result would be that it's a fraudulent transaction, even though that's not really what we would call a positive just walking down the street, but everything else is negative. So keep that in mind. There's no judgment. That's just the way it works. So with a confusion matrix, when it's 2 by 2, it's pretty straightforward. We have true positives, true negatives where it was correct, and then false positive where it was, and false negative where it was incorrectly predicted. So the correct ones are always on the diagonal, and everything off diagonal is false. Now, here's a 2 by 2, but we're going to talk about in the code a 3 by 3. So you see true positive, true negative are on the diagonal. Accuracy, you can actually calculate it from these, the numbers that you get here in a confusion matrix. And of course, the error rate is 1 minus the accuracy. There's some other things, and we're not going to go into detail because for time constraints, but we have recall or sensitivity is the positives that were correctly classified. And specificity is the negatives that were correctly classified. Usually you're not high in both. You get the positives right or the negatives right. There's always a trade-off there. Precision is the proportion of positive predictions that are actually positive. So it's a little different take on it. You see the different parts that are in it. So here's the summary. Like I said, we're going to see this in the examples. But one of the big points that I want to make here is that, well, you can see recall true positives and then add true positive, false negative. So in this case, it's the top row. Now we have to be careful because the code we're using, the positive and negative could be switched. But the true are always going to be on the diagonal. The ones you got right are on the diagonal. So if we have a false negative or a false positive, those are both two different ways of being wrong. So which is the worst way? It depends upon the context and the experience. In a medical diagnosis situation, like in this breast cancer example, if you have a false positive, you're telling someone that they have a cancerous tumor when they don't. False negative is you're telling them they don't have a cancerous tumor when they do. Which one is worse? And you might automatically jump to one of them, but you can argue either one of them depending on your context. But that's something that you have to know going into the model is which is the worst way to be wrong. Is it worse to tell someone they have cancer when they don't? They go through a bunch of expensive and painful treatments that they didn't need to? Or is it worse to tell them they don't have it when they do, when it could kill them when they could have gotten treatment? Most people think it's the second part, but you can argue the other one too. It just depends on your point of view. And in most cases, you can argue either way, which is the worst, but you've got to know. You also, a credit decision. Is it worse to give somebody credit when you shouldn't have, or to not give them credit when you should have? A lot of that depends on the strategy of the financial institution. Are you aggressively trying to get customers, or are you being conservative so you don't want to make mistakes where you give someone credit when you shouldn't have? And spam messages, totally different than breast cancer, right? If you get it wrong, what's the problem? You annoy somebody. So is it worse to label something as spam when it's not, or to not label it when it is? I think most of the models tend to not label it as spam when it actually is. And then it learns as you say, no, this is actually spam. You can recreate the model down the road and include that information. So it's really important to know which way it is. So like I said, we're going to call, in this example, call it malignant positive. So how many false positives? That's where it's predicted positives, but actually negative. So we predicted positive here, and it's actually negatives. So the intersection of that would be the false positive. So there's one false positive. False negatives is predicted negative, but was actually positive. So there's three false negatives in this example. So I say, which is worse? I just was talking about that. So like I said, it doesn't always, it might make both of those mistakes, but you can do things in order to try to minimize the one that you think is the worst mistake. So let's take a look at the code. I need to switch over to that. So we're still in that K nearest neighbors classification notebook. And so there's a couple of ways to do confusion matrix. We can do it straight from the predictions, or we have to create a confusion matrix first and then run it through this other thing to show it. So let's create a confusion matrix called CM, and we use metrics dot confusion matrix. And like I said, we use the true value first, which is going to be the test target, and then the predictions. And then let's just put in CM so we can see the result. And you'll see that's basically the graphic that we were just looking at, except that they're in a different order. But that's not very usable, is it? Because, so what's 73? I mean, you don't really know. So it's much better to just look at it as a confusion matrix. Now you see in my comment here, if you've just installed the Anaconda and all that stuff in the last like 3 months, 4 months, you should be fine. But if you find that this cell doesn't work, then you can use the next cell. I like this way a lot better. So actually, yeah, this turns out to be a little longer example than I intended. But if we look into matrix, we've got confusion matrix display with capitalization. And then we call this dot from, not from estimator, but from predictions. And what we do is we tell it the true value, the test target, comma, and then the predictions, which is preds in this case. And then we can set some other options here. One thing is we can have a labels option, and we can put in the values in the order we want them to be, because we can tell you that the default one that we did, where it was 73.1 on the top row, 337, it put benign first because alphabetical order, B versus M. Whereas I want M to be first so that I have our positive in the upper left-hand corner. There's an option here called color bar. And remember the correlation matrix, the heat map, the color bar is the thing on the right that shows the range of colors. This thing puts a range of colors. It's a heat map. I hate it. It's pointless. That's another thing I want to work on. It does not add to the display. And then I'm changing the color map to grays here. So if you have this and it works right, you'll get that. If you get any kind of an error about from predictions not available or something along those lines, then that could mean that you have sklearn less than version 1.0. And then the next cell has an option for you to do. So you see, this is the same graphic that I had on those slides. All you have to do, if that doesn't work, you can just run this cell and you see you get a different version. There's the color bar. You can't make it disappear in this version, and you can't change the color stuff. So it's just a different way of doing it. And I'll have the code in the other cells where you can do that if you need it. But this way works much better. And like I said, one of the things I want to develop is a better way to do the confusion matrix. It's about perfect in R, but here the colors are totally meaningless. It should not have colors in it because they don't help you at all. So anyway, that's that. Is everybody okay to that point? I think there's only a couple other things we're going to, yeah, just one more line we're going to type in, and then the rest we'll use code that's already there. The other thing is I mentioned the classification report, and it combines all those other numbers that I was talking about, precision and recall and everything, and accuracy and stuff in one piece of output. Now this you need to put inside a print statement, otherwise it's not going to look quite right. But metrics dot classification report, and again, test target the true values. Whoops, target and preds. And so you can do it with just this. In fact, let me go ahead and run it that way. Oh, okay. I forgot these values. For some reason it truncated them to 2 decimal places. A lot of them it'll have 6 or more. So you can say digits equals 4. And I got it inside. I got it in the wrong parenthesis. So you see the numbers are actually more than 2 digits long, but most of the time it defaults to much longer numbers. And you see this here is actually the accuracy of this situation. You didn't, yeah, oh yeah, you did the regular accuracy. If you go up a few cells, you'll see that 96.4549 number. So that's a 2x2. This you can just run the code. This is some wine quality data, and it's got 3 classes that we're trying, 3 categories to try to predict. And this cell has everything, runs a k=5 model, does all the splitting and the model stuff. And so I run that, and I run accuracy. You see it's 90.7% accurate. That's actually pretty good for that data. And if I do the confusion matrix, you'll see it has the same kind of structure. Again, the color is totally meaningless, so it shouldn't be there. But we have the true ones here. We have poor, normal, and excellent. So we got excellent right 4 times. We got normal right 881 times and poor right 4 times. You see, we've got a bit of a imbalance, data imbalance issue here. So most of the time it just predicted normal. So it got 881 normal wrong, but it predicted 12 normals as excellent, and it predicted 4 normals as poor. So it just gives you a graphic way of seeing the results, and then you can get the same classification report. Make it 4 digits. So same thing, there's that 90.71 accuracy. And then this gives you an idea of where it is. So it gives you an idea of some of the better and worse places that it does. It does really well on normal, like we said, but we know that just from looking at the confusion matrix. So this is kind of a tabular version of the confusion matrix in some ways. Does that all make sense? The confusion matrix is a really good way to, like I said, a lot of times it's where it's wrong is a lot more important than how often it's wrong.
Yeah, there's a diagram of the perfect data scientist out there, and it's like a 3-circle Venn diagram.
Right.
And domain knowledge is
Yeah.
a third of that, because you're right. I mean, which is worse, and
Yeah.
what model fits, and yeah, you got to know this area that you're analyzing, or it's just a bunch of numbers.
Yeah, and I mean, as a junior analyst or something, you might do this and have somebody senior help you with interpreting and say, oh, well, we've got 3 here that were predicted benign, but we're actually malignant, and we need to get that number down. And so, like I said, you can look at different versions of the model, and there are ways to add some other parameters to adjust that and everything, but that's well beyond what we're doing. But actually knowing it's an issue is like the most important part. So adjusting it is not trivial, but it's not too bad. So this I'm going to have on the other examples too, the confusion matrix, because it's so you can use it with any classification stuff, because it just tells you. I will tell you as a little bit of an aside is that my students always talk about it's called the confusion matrix because it's so confusing. And it's like, well, the name actually comes from, it shows where the model's confused. So on the diagonal, it's got it right, but it's confused on the other stuff. So take that for whatever it's worth to you. It's another thing that just takes a little time to get used to. And I have to stop every time and say, okay, what's my positive? What did it get right? What did it get wrong? There's nothing wrong. And especially as you get a bigger one with more features, we've done a problem with 4 or 5 in there. So still, the diagonal, everything's good. Everything else is wrong, is a negative result, a bad result. So I just have to go through and look at it. Does anybody have any questions or issues from that? Because what I will do next then is want to talk a little bit my decision trees and regression slides. There's just a few of both of them. So, but let me hit some big topics. I'm losing my pointer. Let me change my share. So let's talk about decision trees a little bit. So decision tree just gives you a graphical process to follow to get to a decision based on the different things intermittently. And we'll take a look at these. And there are regression trees where you can predict a value, but we're looking at a classification tree here. So again, lots of different options. And there's different algorithms. The C 5.0 is the standard in R, and it might be in other packages, but scikit-learn uses the CART, which is an older algorithm that's been modified a little bit, but there's a couple other algorithms out there that are pretty common too. So the idea is that we put, we go back and try to find the purest subgroups in our data. And let me just go to the algorithm. Oh, the strengths and weaknesses. It works on a lot of different problems, and it works on numeric or nominal data. But you can have some weaknesses. And one of the things that we'll see is that it's easy to overfit, especially, and that large trees can be difficult to interpret. We'll see that in the example. They're also called greedy algorithms. The decision tree looks for the quickest solution. So when it's looking at a node to decide where to split, it takes whatever the low hanging fruit is, the immediately best option. Now, that might not sound like a big deal, but whenever we play games and do other things, there are lots of times that we'll say, okay, this might be the thing to do now, but I'm going to take this lesser option because the next step is going to be even better. So the decision tree doesn't do that. So you might see in a team sport like football, you might call plays that don't do much because you're setting up a bigger play down the road. You might see, I play this stupid little matching game on my phone when I'm looking for something. And you might see, oh, I'll take this little one that just matches 3 boxes because it's going to set up one that gives me a bonus thing. The decision tree doesn't see that. And if you think about it, you'll see that we do this a lot, that we take the non-optimum first move because we know the next one is going to be a better move. And that's one big weakness of decision trees, is it'll miss that stuff. So we have splitting attributes, nodes, and leaves, and I'll talk about this a little bit more as I get to the diagram. So what we do is we create a root node, not a root node, a root node, and we put all the data in that node, and then we decide what the best splitting attribute is, which is one of the features. And then we add a branch for the yes and the no, the true and the false. And then we split it into subsets, and then at each of the places we split it, we do that again. And we go until we get to the end, whatever our end is. So if we're looking at credit status, we might look at an example here where let's look at balance, and then we've got good, bad, they're kind of mixed up. Let's not do that. Let's look at age as a splitting attribute. No, that's not so good. We've got good, bad, and that's all mixed up. How about the employment status? Well, we've got good, bad, good. Let's go ahead and say, well, if it's yes employed, those are all good risks. So we could say that's our first splitting status, and we're looking for good credit or bad credit. So now we've split off those 3 examples, and we've split on employed. So now let's take the rest of them and sort by balance and see, well, we've got, if it's a low balance, it seems to be good, and the other ones are mixed, but that looks like a pretty good cutoff. So if we say somewhere around 40, 45,000 something, if it's less than that, then it's good. Now we've looked at those. So now we have just 5 remaining, and we sort by age, which I don't think you can legally do. But for our example, you see that we have a definite split there. So if you're under 43 or 44, 45, somewhere in there, you're good credit. And if you're over, you're bad credit. Again, you can't do this way, but for this example, so now we have all of those examples are categorized somewhere. So this is a graphic representation of that example right there. So this shows that we looked at employed first, and we said, yes, they're good credit. We figured that out right away. If they're no, then we look at balance. If it's less than 50,000, they're good. If it was greater than, then we don't know yet. So we look at age, and we had the last splitting. So employed is in the root node, and employed, balance, and age are all splitting attributes. At balance and age are decision nodes, and then we have the leaves out here. That's where the actual decision is. So that's where we actually decide good or bad credit. We call it a tree, but it goes opposite. You know, a tree usually starts from the ground, goes up. This starts from the top, and at the root node is at the top, and we go down. So we want to get the splitting attribute in order to maximize the information to make the best prediction we can. We can do the Gini index and entropy real easily in the Python stuff. The Gini is the default, but it's just it's a representation of how good the split is going to be. So in both cases, they get kind of similar. So we want that number to be closer to 0 if at all possible. That means that we have relatively what we call pure groups. So I'll show you some of this in the results. So potential problems, like I said, imbalanced classes will really throw off some problems. The Wisconsin breast cancer data, if we did that in a decision tree, it would have really high accuracy, but it wouldn't help us much if we did it like it is, because it would just always, the dominant class would always be where the decision's made. So whatever that winds up, it's always going to wind up predicting the whatever the dominant one is. But we can do some pre-processing to the data to fix that. And the other thing is decision trees, any technique can overfit, but decision trees are really prone to it because it will continue to split until it fits the training data perfectly. And then that will not generalize at all. So I'll try to show you some of those examples. So what we do is we use some sort of stopping criteria, like we'll set the maximum depth of the tree or some other things. We're going to use maximum depth. And then I mentioned underfitting before. If we try to do this big model with all this data with like 2 or 3 features, it's going to underfit and it's not going to work either. The max depth does a post pruning where, I'm sorry, a pre pruning where it just stops after these levels. You can also do it where you create a big model and then come back and prune some of that off. So let me go back, and I'm going to have to go to don't need that anymore, and I'm going to have to go into my master notebooks so that we're not doing a lot of typing. So I'll go into the decision trees. So again, I have a link here. This data is, you might sometimes, if you look at these examples, you might see iris data, which is about flowers. And I see it so often, I hate it now. So this penguins data is kind of similar to it, and it's relatively clean. But it's about, we're going to use the target of species based on the island that the penguin is on and some of these other measurements here, and then the sex of the penguin. Again, we have a male, female, and unknown. So, and I've already got all this stuff run, so I'm not even going to bother to run it. So, and if I wind up going too frantic and fast, get me to slow down. So we look at the data, we've got no problems with it. I had to include all in the describe so that we get the categoricals as well as the numeric. When we create the model, one of the things that I like to do as we're going to more generic is create named constants for test size and random state. And then I can change them in this cell and run it again and then run the model again later. And I don't have to keep remembering what has to be changed. So I'm separating the target and the features here like we did before. The only thing that changed was the name of the data frame. And then I'm getting the one hot encoding using the pandas get dummies on 2 columns, but you just specify the columns you want, drop first. And then we have male and unknown, because female, again, alphabetically speaking, was dropped because it was first. And then we have 2 of the 3 islands. So here you see that this code is the split code, and it's exactly the same as we did before, except that I have those named constants here in order to get test size and random state in here. So it splits. And then again, this common structure of create the tree object, DTC for decision tree classifier. And we have, actually, we don't have to have this criterion equals Ginny in here. And actually, I am going to have to run this because I want to change a couple things. So let's, okay, it already ran because I've got a lot of that stuff in memory. And then, so we can take, you don't even have to have anything in the parentheses here because the Gini criterion is the default, but you can change that to entropy and it'll do a little different, but they're usually very similar. So you see, what's the accuracy? It's 1, so it's 100% accurate. So that is a huge red flag that it's probably overfit. But let's go ahead and take a look at the confusion matrix, and you'll see everything's on the diagonal. So that is the same with 100%. And then you see some of my notes in here. But if we run the actual tree model, this is the description of the tree in text, which that's really hard to follow. So here's a picture version. Now this is, I've done this before with some other models where there's a lot more features, and this model gets huge, but you can see how it just keeps going, and you can't even read this stuff on it, but it keeps going until it gets to pure leaves out there. So that's why it's 100% accurate. So you see, we actually have, I think it's 12 leaves out there, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we're only predicting 3 categories, but it does it 12 different ways because it's all of the different things it's looking at, and it's probably at, oh, and this one is a leaf too, so I guess 13. There's likely that it goes back and looks at some of those variables more than once. So like, oh, if this measurement is less than this, then look at this, what island? It's like, oh, well, if the measurement is part of that other one, then go. So it's not really a very useful result. And so here you see the classification report. This is overfit like crazy. So what I'm going to do is come back here. And yeah, you can put the labels in here just like the benign and malignant, but it doesn't really matter in this case. So what I'm going to do is come back here and add this max depth. And that will only let it go 3 steps down. Now I don't need to rerun all this because my data is all good. I just rerun my model. And what's my evaluation? 98.5%. Now at first it would seem like, well, but we had 100%. But remember, if we wanted to apply this to generalize this to other data, 100% doesn't do us any good. Now in this case, are we really going to have any? Probably not. But if we're using it in one of those other applications where the whole reason to create the model is to look at unseen data, this just is not going to work. So 98.55 is probably pretty good. So it missed 1. But let's look at so now it's a more reasonable decision tree, but there's a much better way to do that. And so that's what this other code is here. So let me get these other comments out of here and we'll see what it looks like if we use Matplotlib. And so we can see, and it's actually a little bit on the small side. This figure size is just something that over time we figured out. So if you can see this, you'll be able to see it yourself by adding these others, feature names, that gives us up here. The first one you couldn't see just had a value up here, but now it says flipper length millimeters. And then filled equals true. It gives us an idea of the different categories. You'll see there's 3 colors because there's 3 categories. So the darker purple, the more pure it is on the Gen2. And you'll see that these, it's hard to see. It has in each of these boxes, maybe this top one, says value equals 114, 54, and 105. That's how many there are in the training data of each of those 3 classes. So this dark purple one here is value 00104. So it has 104 of the Gen2 in there, and it has the predicted class at the bottom, and they don't mean anything here really until you get to the very bottom. So you see the orange is the Adelie, and there's only one that's a little bit, well, no, these 2 are a little bit off, but this is the training data, not the test data. So most of them are pretty pure. And then the green, of course, the darker the green is, the more pure it is on Chinstrap. So this is a lot better way. And there's an even better way, but you've got to install another piece of software and another library and some other things. But so this is a pretty good way to do this. You can see from the classification report, here's our accuracy again. And it was pretty good on well, in some one way or another, it's pretty good on all of them. So it looks like this is a pretty decent model. But is 3 the best value for max depth? If we had a lot more features or a lot more categories, we would probably need a bigger one. But there's something called k-fold cross-validation that we're not talking about, that we can use to find different values of max depth and other stuff. And I'm going to come back to that in a few minutes and talk about that. So that was a tornado through decision trees. Does anybody have a question? And I'll do regression in just a few minutes, as quickly as possible.
Nobody even wants to know the airspeed velocity of an unladen swallow.
Okay. Is that a European or African swallow?
Not even.
So now this, one of the things with the linear regression stuff is now I've kind of got things together as somewhat generically as possible. So here's all of the calls, the same thing. You see import pandas, standard scalar, model selection. Linear model is where we get the linear regression. The rest of it's the same. I've got these couple of display options that you might have run into before that limit some of the output decimals and how many rows show up. And then I mentioned before that we're using this MPG, the MPG auto data. So you can take a look at that. There are some things that have to be cleaned up in here. Horsepower, you'll see it's here as an object, but we know horsepower, it needs to be a number. Well, that's because there are question marks in the data for missing values. So if we reread it with question marks, now it's all numbers. So we can fix that. We have some missing values. We just have 4 horsepower values. So I just decided to drop those. We're going to drop the name out of it. There's some other issues I've done with name in class. We're also going to get rid of year because that's not going to have anything to do with what we're doing. If you use the in place option, remember you can also use as an alternative, you can just save it back in the same data frame name. So I do it both ways, just depending on what's going on. So now our data is good. Let's see, horsepower was a float, so change it to an integer just because it should be. The other thing I mentioned early on when we first talked about categorical variables was that this one had 1, 2, and 3. Well, 1 was USA, 2 was Europe, and 3 was Japan. It's much easier to interpret if it has those values in there. But a lot of people will, as was suggested, change it to the numbers because it looks cleaner, but it's just harder to interpret. Oh, by the way, on decision trees, remember I said decision tree, we don't have to standardize data. If we did standardize the data, it would give us the same decision tree, but instead of saying, like the measurement in millimeters being less than 106, it might say less than minus 2.135 because it's a standardized value, and it's real hard to interpret it with that. So it doesn't ruin your model if you standardize it, but it does make it a lot harder to interpret. Now, in this case, I looked at a correlation matrix with all those options I told you before, because we could have a multicollinearity issue where we have a couple of the features have the same effect on what we're looking at. So not surprising that displacement and cylinders have a high correlation. If you know anything about cars, and I don't know that much, but cylinders is the number of cylinders that you have in your engine, usually 4, 6, or 8. I think there's a couple other options. I have a Harley, it has 2. But the displacement is the total volume of those cylinders. So yeah, they ought to be pretty closely correlated. And one of the things that we'll do is drop one of those in order to try to make it a little bit better model. So in this case, since cylinders has certain set values and displacement is a decimal value, let's just drop cylinders. So do that too. So now got data that's in pretty good shape. So we need to use one hot encoding on origin. So now we dropped Europe because it came first alphabetically, and we have origin Japan, origin USA. And then we can standardize because if you look at them, not surprising, weight and some of these other items are on grossly different scales. So here's what I was talking about, getting to some standardized code. So I've also made the label name for what's our label for our target, and then setting just a generic data frame name, DF, to the name. So if I make the changes in rows 4 through 7 to whatever value I need, I can run the rest of this code as is. You don't have to change it at all. So if you put in what's the name of our target, actually that should probably be target name. I've been using label name for so long I didn't even think about that. But that's going to be the target column that will separate it here. Out of the data frame, I've got just the generic DF there, and then test size and random state. So when I run that, I've created the model, or I've fixed all the data, so the data is ready to go. And now I can do just like I've done before, create the linear regression object, use fit and the train and target data. I put in this X, capital X and little y, because you'll see that sometimes in examples. Instead of train features, it might be train capital X. The capital X, little y are used a lot in the statistical side. So if you see that, that's all that is. Y is the target, capital X is the features. And then use predict in order to get the on the test features to get the predictions. We can do testing and evaluation. Here on the testing, because it's a number, we use mean squared error, and we want to get the lowest one that we can get. Now, is 15.016 the lowest one we can get? Well, there's a whole other process that we're not doing here that we could go through, and we could run different values of test size, different random values, different combinations of the features in the model, and try to find the one that's the best. So that whole thing is at least finding the different combination of features is called feature selection. That's a whole separate thing. I do in class run a recursive feature elimination thing that's built in that does some of that, but we don't want to mess with that. So this is a basic linear regression, but it's just one model. And that actually, if somebody has a question, go ahead, but it actually leads me into my last things that I wanted to talk about. And that is, where did that go? Why is my, oh, I've got that off the, move that up. We can look at, we've looked at models that had a single K value, or a single max depth, or a single value of the random state, or one of the other parameters. But those are the parameters, those are the hyperparameters. They're outside the method. They're the things that we set beforehand. So the parameters are the ones that are determined inside the method, like those regression coefficients. We didn't actually look at those, but classification probabilities and other stuff. So the point here is that we can tune hyperparameters. You can go back and run that K nearest neighbor or decision tree with a different max depth or a different K value, get the accuracy and compare them and see what works. Like I say, you can use different random state values to get different splits of your training and test data. You can use that K-fold cross-validation. But remember that if we look at all that and look at the test data, and then we use that to decide which is the best data, that means we no longer have unseen data to use for our evaluation. So what we typically do is, instead of just having training and test data, we'll typically look at 3 sets of data: training, validation, and testing. It helps if you have a lot of data, obviously, and you can split it up. But my point that I'm trying to get across here is that there are lots of things. We've talked about a lot of stuff here in this time, but there's tons and tons of other stuff out there. I've mentioned cross-validation, and pipelines is a way in Python where you can automate some of this to try to find what but with code where you could rerun it and you can find what's the best K value or what's the best split. And the whole feature selection is a whole other topic that you have whole books written on. There's also market basket analysis, text mining, neural nets, support vector machines, naive Bayes, lots and lots of other techniques that I haven't talked about.
Can you,
If you want more info, these are 4 books that I think are pretty good. My favorite is the Python Machine Learning on the upper left. Sebastian Rashka and Vahid Mirja Lili, something like that. I don't know. One of the things that these 4 books have in common is that they are all, I think, $40 or less on Amazon. So pretty good. The ones on the right are just about code. So if you know what you want to do and you want to get some code, those are good examples. Of course, you can also search online, but the Python Machine Learning, and there's a different version that's got a slightly different title that goes into, I think more, this one has some TensorFlow stuff in it, but it goes into more. It's a pretty thick book, but it's got lots of stuff about, you know, how you do a K nearest neighbors and how you do a K means and all that stuff. So those are good places for some information.
hey, Mike, can you back it up 2 slides? There's about use a third training.
Yeah.
Training validation.
So
and
we've been
testing.
using training and testing. It really is better if we use 3 data sets. So we have a training and validation, and we use those the way we've been using training and testing, and we get the best model. And then we use our unseen testing data to see how accurate that model is likely to be on unseen data.
And then,
But we don't make any changes. If we make changes to the model, now we've used that data to change the model, so we no longer have unseen data. So we use training and validation and to make changes in the model and try to get the best efficiency or, you know, best false positives or whatever it is that we're looking at. And then that final testing data just gives us an idea of how accurate it should be out in the real world.
and that's where you would inject, if you had another set of data while you're running that notebook and everything's in memory and the model is trained, that's where you would come in and
We've got our
inject
final model. Yeah,
and
you can
inject
do
a
that.
real world.
Or you can always save the model using pickling and open it up in a new notebook and apply it there.
That's next level.
Yeah.
Okay.
And one of the things, you know, and you guys have probably been doing this, but what I always get is do all the data prep, all the general data prep and stuff in a separate notebook and save it and then import it and do your modeling in another notebook. It just makes it a lot easier to go back and forth. Otherwise, you can have this huge, yeah, my hands are even off the screen, this huge notebook, and it's hard to find individual parts. Of course, if you use the table of contents and some of those other add-ons, it's a little easier, but still. Anyway, so I feel like my jaws are on fire because I went through all that so quickly there at the end. But if anybody has any questions, like I said, I'll pass on. It'll probably be later this afternoon, but I'll pass on those completed notebooks. And oh, I guess I actually didn't get to my last slide. Just has exactly what you would think that it does. It has oh, now I'm all messed up on my screens and stuff. It just has my you know, name and contact information and email and stuff, but that's in all the notebooks too, and I think on slides, so it's in enough places, and you have those slides, so so you got that available.
So that is next level. So folks, I would like for y'all to think about applying that if you by chance want to spend some class time, because we've got 3 more sessions and only a couple of topics to cover. So if you wanted some more time to apply Power BI, great. If you want to run some work data through these machine learning techniques and see what you see, we might be able to spend some time doing that. Any questions for Dr. Ellis before?
While people
Questions,
are thinking and unmuting, so you mentioned Power BI. I've done a bunch of presentations at conferences about using Python, but one of the things we're going to do, I'm going to do with a couple of my colleagues in my department this fall, is we're going to do a comparison, take a couple of these problems and do them in Python, R, Power Build, no, not Power Builder, Rapid Miner, and Power BI, and compare, and then look at, if you're trying to decide on what to use to teach people, what's the best, what's being used. One of the things we did was we went out to all of our employers a couple of years ago and asked them what kind of tools they were using, and there was no standard. And so that's what we decided first to do it some in R, and now we're doing it in Python, and we're trying to do some other things. So yeah,
Are
all
you-
the concepts are good, and no matter what tool you use, it just depends on how you do it.
Yeah, I'm just trying to think of how you would avoid bias in that study, because there's levels of comfort with each of those tools. If you get a really good Python expert doing it in Python, they
Yeah.
might be better than a mediocre or beginner Power BI guy, or vice
Right.
versa, you know.
Well, we're aiming it at people that are maybe relatively new to teaching this, and they're going to teach it to students that don't have any background in any of these tools necessarily. So what are the pros and cons? And it's not going to be a rigorous study, well, at least not at first, but what are some of the pros and cons? And I've got one colleague is good with R, which I've done before too, but I'm going to do Python and Rapid Miner. And then another colleague has some Power BI experience, so she's going to do that. So,
and then we could bring Whitney in, who was doing pure Tableau. There's a Tableau training pass where you can attend quite a bit of instructor-led content for one low price.
yeah, that might have been what Dr. Thomas was doing this summer.
Now there's camps out there. I'm not going to learn R. If that limits my what little career I have left, then so be it. But Python is so universally applicable in data engineering and web development and computer science that I just forget it. R has naturally clustered itself down into the data science statistics world and nothing else.
Yeah.
So as a generalist, there's no way I'm going to spend a whole lot of time learning it.
And I still use R for structural equation modeling and other stuff on research projects, but on all this kind of stuff, anything with data, I use Python. In fact, I've gone in and cleaned up the data in Python and then run the analysis in R on things that are not readily available. Although a lot of that stuff is getting available in Python as well.
Yeah, there you go.
I find it to be fun. I find Python more fun than R.
Okay, guys, any parting comments? If not, questions?
I think this was really interesting, and I appreciate you taking the time to show this all to us.
Well, thanks. I'm sorry that I had to rush through everything at the end. Like I thought I thought I was going to be done by 11:30 with everything, and that's unfortunate. But
well, luckily YouTube has a play at half speed as well as a play at double speed, and this would be one of the few times that I would want to slow it down. No, Mike, your expertise is obvious and really appreciated. Like I said, I lean on your stuff. I've been talking about you all it's not a semester, all cohort long, and I'm really glad that you had time this summer to take out of your schedule and come meet with us and show us some of this next level stuff.
Like I say, I just find it to be so much fun to mess around with this stuff.
And when you finally get it to work,
I'm sure there's one or two in the group that'll probably have the same thing, and others are like, oh my gosh. But but that's the other side too, like you were saying before, Don, is like, and I mentioned, just because you can do something doesn't mean you should. There's plenty of insight you can get into data without having to run a machine learning model, as you said, with Excel, just by sorting stuff, for crying out loud. So yeah, you don't have to jump right to doing a neural net. And unfortunately, there's lots of things that I see that's what they do, is they jump right to, let's do a neural network. It's like, you don't even know. Experts don't know what goes on in a neural network. So why are you doing that?
Yeah, and I always fall back to the, a lot of managers will kind of go, well, what's the data? We got all this data, social media and all these systems. What's the data tell you? Well, what do you want to know?
Right.
Yeah,
so let's at least have an idea of what we're looking at.
There you go.
Yep, that's that first step in the CRISP DM, the business understanding.
What do you want to know?
Yep.
Okay. All right, guys. I appreciate it, Mike. And we'll see everybody 8:30 Thursday morning.
Okay.
And I'll post.
Thanks,
those.
everybody.
I'll post the completed notebooks.
Okay.
All right. Enjoy the
Thank
rest of your day, everybody.